Good evening, my dear warriors. Welcome to the marathon, the physics marathon for your class 12th wave optics or light waves chapter. And today I'm going to start from the basics because many people might be learning this for the very first time. So we are going to use the concept of 11 standard waves. So that part you should know. But yes, from the 12th standard perspective, it will be from the basics. And we are going to deal with, the concept of wave, the concept of interference, and, the Huygens principle. Then we will go on to Young's double slit experiment and the variations. And then we'll go to diffraction and finally polarization. That is the flow of today's event. And I'll be taking up some problems, but yes, we'll be predominantly focusing on the concept, the theory, and the application. And yes, couple of problems as well. So get ready, guys. And this is going to be a long session. Welcome aboard, Sabrinath, Yashwant. Welcome, Vihan. Welcome, Jaitra. Welcome, Pradeep. Good evening, guys. Good evening. Nice to see all of you back over here. And I hope you guys are doing great and having a fabulous time out there. So it's time to begin with the class and start. Yes, yes, start this particular marathon. I hope I'm audible and visible to all of you. Yeah, that's my quick introduction. If you are new to the channel, say hello, subscribe if you have not yet subscribed. And once subscription is done, mark your attendance by liking this video. Okay? Hi Harshini, hi Aityan, welcome aboard. Hi Bhanushri. And how many of you are learning this chapter for the very first time? Let me know quickly in the chat box. How many of you are seeing this chapter for the first time or barely done anything? Barely done. Sir, I have not understood the concept. So if you are one of those, today's lecture will be very fruitful for you. And if you have already done most of the chapter, it is a good revision also. Yeah. All right. Great. So let's begin with the class. Hi Nitesh. Good evening. Good evening. Now, before we go ahead, remember that the entire PDF and everything will be available in the description box of this particular video. So after the session is done, right, you can go down into the description box and you can see this particular link is there. Ask with any doubts. So open that link and on the right hand side below over here, you will see something like description. Click on that. After that, you will see basically download PDF, smart notes, quiz. All options are available. So Ved will create its own notes. Ved will also create quizzes on this particular topic. Ved will also give you, all doubts which you have in case after the class also. And yes, whatever I write will also be available in the PDF format, after the video is over. Okay, so that is going to be there over here. Ask with any doubts. That's the link that you'll have to click. Now, what is this chapter all about? See, imagine there is a lamp. Imagine there is some obstruction. Imagine there is a screen and all of this is in a dark room. What do you think will happen? And what do you think you will get on the screen? What kind of image, what kind of pattern do you think you will get on the screen? Let me know quickly in the chat box. Yeah. Now, if you think that light travels in a straight line, which is also true, and light follows the geometrical path and it will cast a shadow, which is what one would expect if you considered light like particles. Imagine there were particles of light, then the particles of light will get obstructed over here. The particles cannot propagate ahead. So you will see a dark region on the screen, which is called as the shadow of the object. The rest surrounding area will be bright because the light particles are reaching there and you will see a shadow over there. That's what you should expect. That's what we have been taught also most likely. But surprisingly, when Young's did this kind of an experiment back in the days when Newton was there, they found very ridiculous. They found a very ridiculous, outcome. What they saw was actually in the between of that shadow, exactly over somewhere here, they found a bright spot. It's also known as the Young's bright spot. People were surprised that this object is completely solid, so you should get a complete dark shadow. There was no hole There was no pinhole. There was no, cavity in that particular object. How on earth did this bright spot appear? Then it took hundreds of years for people to realize, although it was proven that time, but nobody accepted, because Newton said light behaved like particles, and he called these particles of light as corpuscles. And going against Newton is like going against your school principal. You don't say no, even if she is right, wrong, whatever, you say like, okay. Same way, people were afraid of Newton. So even though this experiment proved that light can't just behave like particles, there is something more to it, people did not accept it that time. Later on, people understood that this kind of phenomena, this bright spot, can only come if light were to behave like wave. And then it was understood light has dual nature. Sometimes it shows particle behavior, in some experiments it shows wave-like behavior. And when light behaves like a wave, even though there is an obstruction, the light bends from all the sides and it creates a bright region due to a phenomena known as interference. Just like if there is some obstruction in front of you and somebody is talking behind, okay, then you can still hear what the person is saying, because sound travels in the form of waves, it gets distributed, it spreads all over. Similar phenomena is occurring in the case of light. So this is not what you should get. This is expected, but this is not what you actually get. What you actually get is this. Isn't this fascinating? And if it is, put up a fire emoji quickly in the chat box if you never knew about this. Yeah. Hi, Fast Furious, Ritish, welcome. Hi, Teja, good evening. Yeah, and concentrate, guys, on the class, please. Yeah, very good. Excellent. So, basically, light does not necessarily go in a straight line, basically rectilinear propagation. Rectilinear means straight line. Ray optics. So that was the previous chapter, ray optics. Light travels in the form of rays, ray diagram. But it is only true till some extent. Whenever light encounters a different medium, whenever light encounters a hole, whenever light encounters an obstruction and it interacts with the matter, then you will see that there are wave-like characteristics also which are exhibited, which are shown. So, in a normal situation, when there is a small hole, now imagine this object has a hole, okay? So, what you should expect if light is coming from this side, the light should pass through that hole and you should get a bright spot, isn't it? This is what the expected observation should be. Yeah, it should pass through it like particles. If Newton's corpuscular theory, corpuscule means particle of light, that is what Newton thought light was. Okay, but that was wrong. In that day, Newton thought light is like particles. Yellow color is of different size, blue color is of different size. He thought that these light sizes, particle sizes decide which color it is, which is obviously wrong. Anyways, so this is what one would expect. But what happens is, in reality, when you pass light through a small hole, you will get rings, which feels very unnatural. How the hell did this happen? So this happens because light behaves like a wave, and the waves of light go around throughout this space. They create interference patterns, and that's how you get bright and dark regions, and you get alternate bright and dark rings. So this is the actual observation, not this one. Adjusting the size of this hole and the wavelength, one can change the size of these rings and the spacing between them. But that's another part. The point is, you will not get simply a bright spot. You are going to get alternate bright and dark rings. That is funny because one would expect light to be like a particle, but it shows wave-like behavior. By the way, anybody knows what this phenomena is called? Put up the answer in the chat box in case you have heard about it. So when light travels through a hole or an aperture or through an opening, then the light spreads, interferes, and causes a pattern on the screen. This particular phenomena is called as okay, yeah, it's called as, yes, it is not interference, it is interference only in a way, but it is called diffraction. Yeah. So why is it small? Because other places that interference is dark or destructive, that's why it will create a dark shadow around it, but only at a particular place where in constructive interference happens, you will see a bright spot. That is the reason for it. Okay, I hope that is clear. Hi Kritish, thank you so much for that compliment. All right, Afia, Harshni, yeah, it is interference in a way, but it is called diffraction. Diffraction is the phenomena when light passing through a hole or a small aperture, it spreads, bends, distributes, and then interferes and then produces some pattern like the ring or whatever. Okay, so that is called as yeah, basically diffraction. Focus on the class. Focus on the class, man. Yeah, Ritesh. Okay. Yeah, focus, focus, focus. All right. So now that we understood light is a wave, one of the first ideas of this wave concept was given by Huygens. Although his theory was not completely correct, but it was not completely wrong also. There are some good things about Huygens principle and Huygens wave theory. Like when you meet a person, there are some good things, some bad things. We should ideally neglect the bad things about a person. But unless the bad things are too many, then you cannot neglect. But the thing about Huygens principle is that he was able to explain many phenomena like reflection, refraction, interference, and you can also see how light bends. He was able to prove Snell's law and all of that. So that is why Huygens theory is still studied today, although whatever he proposed actually never existed. So, what did Huygens suggest? Huygens said that light is a wave, but not any ordinary wave. He said that light is basically a mechanical wave. Okay, so he basically said that light is not just any wave. He said light is a mechanical wave. What is the meaning of mechanical wave? Mechanical wave means it needs medium, and without that medium it can't travel. Like for sound to travel we need air, correct? For the ripples on the water you need water, correct? Light, we know it actually does not require medium, but Huygens said like that. I am not saying it, today's world will not accept it, but okay, that is the bad quality, but we'll ignore it. In that times, I mean 300 years back, it's okay, man. Like seriously, medium he called it is ether. Now see, you made this statement and made the whole scientific community mental after this. When Huygens said that light is a mechanical wave traveling through a hypothetical medium called as ether, everybody, and because he was able to prove other things also, everybody started to look and find out where this ether is. But nobody was able to find it. Everybody conducted experiments, dedicated their lives, sacrificed their lives, but nobody was able to find this ether. It actually never existed. And that's what Einstein proved after so many years. And Einstein was like, bro, chill. There is no such medium as ether. And he gave the Einstein's theory of relativity. And he was able to talk about how the speed of light is constant no matter what the medium is and where you are, how you are moving. So he was able to prove that. And hence he was, regarded so much. So many people wasted their lives, but ether was never ever found and it is not existent actually. Isn't it amazing, guys? Sad life. Yeah, happens. Hi Joshi, welcome aboard. Yeah, good evening, guys. Yeah, he said that the space is made of ether. Actually, if you think about it, you know what, I would also still believe it. I mean, I have always thought about this. What is there around us? Well, it's air, you might say. But what if I remove air, like in outer space? There is nothing, vacuum. But what is that vacuum? Is it proton, neutron, electron? It's nothing, right? It is basically nothing. So, what is that nothing made of? Think about it. What is the nothingness in this universe made of? Sir, it's made of nothing, meaning there is nothing over there. But I feel that nothing should be also something. And that something is what Huygens said is ether. But that something was actually nothing. That's what Einstein said. I hope you did not get confused, but it is really interesting. If you want, replay that. It feels very confusing, it feels very comic, but if you think about it deeply, you will understand what I'm trying to say. How many of you got it? Good evening, good evening, good evening. Yeah, that zero is also something. Like when your teacher says you are a zero, you are not hero. But that zero is also something. That something is ether. But that ether was not there. Crazy, right? Yeah. Oh, you two had the same doubt. Guys, we think alike. I'm proud of you guys. Proud of my warriors. Amazing. Anyways, so he gave the wave theory of light. And then what he said was very simple, guys. I will just show you what he said. He said, okay, you might have seen drops of water falling on a lake or in a tub or on a pool of water, something like this. It falls. What happens? You will see ripples of water. You will see ripples of water, something like this. This is the side view. Yeah. You will see ripples of water like this. If you turn it off, it will go. Yeah. So if you turn on the tap, you will see ripples of water going like this. He said in that hypothetical medium, this water is that hypothetical medium he called as ether. When you turn on a light, or let's say I'm turning on the torch like this, that torch, that candle, that lamp, whatever it is, that is basically the source of disturbance. Like the tap over here is my source for the wave. The light source is the one which is causing the disturbance in the medium, and the disturbance propagates with a constant speed in the medium. If the medium changes, that speed also changes. If instead of water it is alcohol, it is different. If it is star, it is different. If it is sauce, different. So the manner in which the wave propagates changes, the speed in which it propagates changes if the medium changes. But in a particular medium, the wave will propagate with a constant speed without any acceleration. And any of these disturbance if you look at it from the top, you will see it is going in all the directions. All these points have that disturbance reaching them at the same time. So these are called what? Wave front. So the wave front is going to expand. The wave front is going to expand as the disturbance propagates. So the disturbance reaches all these points at the same time, and that is why all those collection of points is called as a wavefront. Is that clear? Is that clear? Bro, this is not iPhone 17 Pro Max. I am teaching light waves and this thing. All that you saw is my phone. This is old phone. You know how antique it is. It is going to be in the museum now. Yeah, this is very old. I changed my phones only after 6 to 7 years. Very old phone. It's almost now 6 years, I think. Yeah. Okay. This is clear, sir. I understood. So what is the meaning of wavefront also? So wavefront is basically the locus of all the points where disturbance reaches together, where the disturbance reaches, where the disturbance reaches simultaneous, where the disturbance reaches simultaneously. And the source of light, and he said that the source of light, the source of light, the source of light causes that particular disturbance, which moves in that medium with constant speed. In a particular medium, it will propagate with a constant speed. So that is basically Huygens idea, what he proposed. I hope this is clear. Amazing. Yeah, this is one short lecture, Suchi. Tra. Yes, this is one shot only, one shot marathon in detail. I'm going every topic detailed so that after this lecture, you will not have any doubts. So all the points on the medium where the disturbance reaches simultaneously and they go up and down, they oscillate, they oscillate together. It's not like one is going up, one is going down, one is going up, one is going down. No, no, no. They oscillate together. All these points are then called wavefront, is the locus of all the points at which the wave disturbance is in the same phase. Phase means situation. Phase means situation, condition, situation. It is a bad phase, it is a good phase, like that. Situation. So in physics terms, phase is that situation of that particular body object particle. Yes. All right. Perfect. So if you remember, wave equation which you have studied in 11th standard, this is a quick recap of that. Any wave which is moving in a direction follows this particular equation. You have studied this in 11th standard. Y is the displacement which it goes up and down. A is the amplitude. Sine or cos, you can use anything. If it is sine, it will go like this. Cos means it starts from the top. Sine starts from 0. Cos will start from the top. Positive one. Omega t plus or minus kx. What is this omega called? Omega is nothing but angular frequency, which is 2 pi into frequency, or basically 2 pi divided by time period. K is called as the angular wave number, which is nothing but 2 pi divided by wavelength. 2 pi divided by wavelength. Is that understood? Remember this formula? The y coordinate, which is basically how much up or down it is at any given instant or place, is amplitude. This is nothing but your amplitude. This is nothing but your amplitude into sine or cos omega t plus or minus kx. If you remember correctly, then you will also remember that positive means it is going in the negative x direction, and if at all there is a minus sign there, then it is going in the positive x direction. It is exactly opposite. If it is negative, then it is going in the positive direction of the x. So the wave is going like this in the positive direction. If it is positive, then the wave is going in the negative direction of x. That is what it is. And this omega and k also give you the wave velocity and all of that. So remember, wave velocity is omega divided by k, which is also frequency multiplied by wavelength, which is also frequency multiplied by wavelength. This v is nothing but your wave speed. With what speed is that wave going? Is angular frequency divided by angular wave number, or frequency in hertz into wavelengths in meter. Simple. These are all 11th standard topics which I'm trying to revise for all of you. Perfect. Amazing. Amazing. Okay. My haircut costs more than what the lecture cost is, because this lecture is absolutely free, no? So this haircut, it costs more than that, man. Okay. But I hope my haircut cost is lesser than your marks, because I don't want your marks to be lesser than my haircut cost. Then I will feel very bad. But I'm telling you, my haircut costs less than 300 only. Okay. So please try to score more than how much ever my haircut cost is, or else I'll feel very bad. Then I will start growing my hair. I will not cut it only, or I'll go for a very expensive haircut. Okay, bro. Now that we have understood what a wavefront is, what a wave is, what is the wave equation, just a quick revision. Now, Huygens gave a theory by which you are able to construct how the new wavefront will look like after a given point of time. And that is called as Huygens construction. So, as per that theory, I will just explain that. Imagine at some given point of time, I know this is my wavefront, or let's say this is my wavefront. So this particular wavefront is called as the initial or primary wavefront. And I know for a fact that let's say my light is going in this direction. This is the direction of propagation. Direction of basically light. It is going somewhat like this. So after some time, if I want to figure out how the light will look like, what I should do, sorry, how the wavefront will look like, then what I should do is, you should take many points, we should take many points on the primary wavefront. In fact, infinite points, ideally speaking. But even if you take some 100, 200 or 7, 8 points, depending on how big the figure is, okay, it's okay. These points, these particular points over here, these are called, they are called, the new sources on the primary wavefront. They are called as secondary sources. They are called secondary sources, which means all the points on the wavefront, all the points behave like new sources. They are called secondary sources. What will the secondary sources do? These secondary sources are now going to create secondary wavefronts, something like this. A wavefront like this. This will create a wavefront like this, and so on and so forth. So they will start creating secondary wavefronts in this particular manner. In this particular manner. Now, these secondary wavefronts, interestingly, these secondary, these particular secondary wavefronts, these particular secondary wavefronts are produced by the secondary sources, in the direction in which the light is going. They are not produced backwards like this. Why it is not produced? That was not explained by Huygens, but later on mathematically it was proven why it does not happen. But Huygens did not explain why it is not produced in the backward direction. Okay, it is only produced in the direction of which the light is moving, not on the other side. And he also said one interesting thing. He said, if you measure the radius, if you measure the radius, the radius, the radius, that particular radius happened to be c multiplied by t, which is nothing but the speed of light, speed of light, speed of light multiplied by time after which new wavefront has to be obtained. After 2 seconds, I want to see what's the new wavefront. I'll put time as 2. After 1.5 seconds, I want to find how the new wavefront will look like. I'll put the value of time as 1.5. C is your standard speed, which is 3 lakh kilometers per second, or 3 into 10 to the power 8 meters per second. That is the radius, because it's obvious that speed into time is going to give me distance. So that is the distance which the new wavefronts will propagate in all the directions. Just imagine, if you have a source, it will move ct distance in all the directions. So the radius of this wavefront will be obviously c times of t. Is that absolutely clear, my dear warriors? Excellent. Then what he said was, you draw a common tangent, you draw a common tangent to all these wavefronts. You draw a common tangent to all these wavefronts. That becomes your new wavefront. That becomes your new wavefront after after time t. That's it. So if you want to find the new wavefront after time t, that's it. You draw the common tangent. So the steps are simple. If you know the original wavefront, take all the points, behave like secondary source, then all of them will produce secondary wavefronts of radius ct everywhere. Draw the common tangent, that will give you the new wavefront. So that is basically Huygens construction. Huygens construction. Primary wavefront, secondary sources, secondary wavefronts, the final new wavefront. That's it. That is what it is all about. I have explained it in a very understandable manner. Everybody simply will be able to get it, because in JEE, that's what you will need rather than by hearting the theory. How many of you understood this Huygens principle? How many of you understood what Huygens actually meant over here? What is wavefront? Okay. Yeah. So Huygens was the real OG of our Huygens was our real OG of our, what do you say? Wave theory. The final person to talk about waves was Maxwell, that came in 1900. So he's basically our OG. He's really cool. Yeah, he's really cool. Yeah, amazing. So that was Huygens principle. So maybe we can start looking at some questions coming up on your screen. Okay, here it is. Oops, 1 second, guys. Okay, yeah, here is the question. According to Huygens theory of wavelight, which one of the following statements is not correct? Different colors of light are due to different wavelengths. Different colors of light are due to different sizes of corpuscles. The speed of light in denser medium is less than that in rarer medium. It can explain laws of reflection and refraction. Which of the following statements are not correct? Come on, guys. This is very obvious. Everybody should be able to get this. Spam the answer in the chat box. It says which of the following is not correct. Not correct. Huygens was popular even till, or rather is popular even till today, because although there were some wrong assumptions and bad things about his theory, it was able to explain many things. And I told you, he was able to explain laws of reflection, Snell's law, refraction law, all of that. Speed of light in denser medium is less. Yeah, in dense it is less, and rare medium it is more. That is again Snell's law. He was able to prove it. So he was able to explain refraction. So this also was the correct thing. Different colors are due to different sizes of the particles or wavelengths. Wavelengths. Wavelength is wave theory. Corpuscles, corpuscles, corpuscule. This particular concept comes from Newton. This is from Newton and not from Huygens. So the question is on Huygens. Hence the answer is obviously option number B. Is that absolutely clear? I've explained other points also. It's not about just marking the answer. You should know about the other points as well. Okay. So let's see if you can construct this particular thing. This kind of questions have come in the JEE exam many times. So let's see whether you are able to solve this. There is a concave mirror. Okay, there is a concave mirror like this. There is a concave mirror. And what happens is there is a planar wavefront. There is a planar wavefront which is going like this in this particular direction. In this particular direction. What will be the shape of the wavefront? What will be the shape of the wavefront after it has been reflected? What will be the shape of the wavefront after it has been reflected from this particular concave mirror? That is the kind of question which is asked. Okay, so think about it. This particular wavefront will keep on propagating, It will go like this also. It will eventually reach here. It will reach here also. And slowly it will start reflecting one by one. Now, what will happen after that? It might look confusing, but I'll tell you one thing. If you take any wavefront, if this is your wave front, you also remember rays of light. You also remember rays of light. Rays of light are going to be always perpendicular. Rays of light are always going to be perpendicular to the wavefront. These are the rays of light and they will be always perpendicular to the wavefront. That is very important concept and I will use that concept over here. How exactly? Observe now. So forget all this. We don't need all this. Okay. Just think of rays of light now. Just think about rays of light. So the ray of light will go like this. This ray of light will go like this. This ray of light will go like this. And this is a parallel beam of light. What happens to a parallel beam of light? After reflection, it will pass through the focus. It will pass through the focus, isn't it? So it will pass basically through the focus of that concave mirror. So now you just have to draw a perpendicular to the reflected light. So if you draw the perpendicular to the reflected light, it will look something like this. It will look something like this. So this is how it will look like initially, and then it will go like this, okay, point, and then it will become like this, and then like this. So this is how it will look like. Yes, these rays are going in this particular direction. These rays are going in this particular direction like this. This is how the new wavefronts will look like after the reflection is done. Is this clear? So the parallel goes like this, hits, and it becomes curved, curved, curved here, and then it becomes bulged out over here. So this is how the wavefronts will look like after reflection. Is this clear, everyone? Okay. Oh, I draw well. I'm an artist. Yes, I'm an artist. Every physicist should be an artist. Every teacher should be an artist. Else you won't be a teacher, right? But not that kind of artist. If you are expecting me to draw some beautiful paintings and all, no, sorry. Diagrams, yes. Okay. Now there are three kinds of wavefronts that you can expect. See, guys, in bulbs also, you might have seen different kinds of bulbs, like a tube light. It's a long, slender, cylindrical body, or a simple bulb, round shaped bulb also. Sometimes you might have seen on the ceiling, like my ceiling has it. Unfortunately, I cannot show it to you, but yeah, it is there unless I can move the camera up. It's a planar wavefront. Let me see if I can do it. First time today, Shreyas Sir is going to tilt the camera and going to show how it looks like on the top and how bright and crazy it is, guys. Isn't it crazy? Yeah, so that is what kind of source? Yeah, what kind of light is this? This is a planar source of light, isn't it? Oh, crazy. Okay, second. So that is your planar source of light. So there are three kinds of there are three kinds of light sources that we study in our JEE syllabus. First is spherical or point source, meaning the bulb, the light element which causes the disturbance is like a point or a sphere, and the wavefronts envelope it, cover it in spherical manner, and they propagate in all directions, front, back, left, right, top, bottom, like spherical shells, which are constantly growing in size. So that is a point source or a spherical source, and they keep on expanding their spherical wavefronts in all the directions. So a spherical wavefront is observed, for a point source. You can see the rays of light are radially outwards, and they are also perpendicular to the spherical wavefronts everywhere. And the direction of propagation of light is radially outwards and perpendicular to the wavefront at any given point. Okay, so that is the concept of a spherical wavefront, which is created from a point source. Keep that in mind. Next, you have the planar wavefront. Oh, okay, before planar, we'll do cylindrical and then we'll go to planar. Yes, cylindrical wavefront. Imagine like a tube light. It's a long, slender body, or you can call it as a line source also. So the line source creates wavefronts which are cylindrical in nature. The size of the cylinder grows only radially, not height-wise. So you can see the rays of light are going radially, not up or down. And the size of the cylindrical wavefronts keeps on growing radially. And that is why cylindrical wavefront is observed from a line source. Example, a tube light. The direction of propagation of light is radially outwards, and obviously has to be perpendicular to any wavefront that you take. Are you able to visualize this? Yeah? Are you able to visualize this? Yep. Yeah, board marathons will come, man, later on. Not now, but it will come later on. Perfect. Next, planar wavefront like the one I just showed it to you. Unfortunately, I cannot move my camera again now. It is not so easy, guys. Yeah. So planar wavefronts, like the one on the ceilings of many houses, hotel rooms, and airports, and so many places. So it is a plane source. The wavefronts are also planes which keep on moving front, front, front like this, and the rays of light are parallel to each other. So the planar wavefronts are observed when the source is very far. Basically, when you are really, really far, then what happens? The curvature disappears. Imagine there is a bulb which is 100 kilometers away. The light coming from it, when it reaches me, is almost plane. Yeah, it's a big sphere, but if you consider a small part of that big sphere, it's almost plane. Or you can say the source is at infinity, or it is a planar source itself, or basically a planar source, or basically it has to be a planar source. It has to be a planar source of light, and the direction of light is perpendicular to the plane wavefronts as well. Very good. Now, one interesting thing to note is about their intensities. You should know this by heart. Tell me, oh, by the way, what is intensity in case you have forgotten? Let me remind that also to you. Intensity of light, we have done it in modern physics also. So if you talk about intensity of light, intensity of any light, it is nothing but how much energy is flowing, how much energy is flowing per unit time, per unit area of propagation. So what happens is the unit, SI unit of intensity, the SI unit of intensity becomes, this is joules per second, joules, joules per second per meter square, or joules per second is watt. So watt per meter square is also fine. So watt per meter square or joules per second. Another thing is that if you have your light wave, the wave is going like this. This is the amplitude. Actually, light is an electromagnetic wave. So this wave is actually the electric field or magnetic field. So whatever is that particular amplitude, right? Whatever is that particular amplitude, this is true for not just this wave, any kind of wave, sound wave, earthquake wave, water ripple wave, any kind of wave. You will see that the intensity of the light is directly proportional to the square of the amplitude. So if amplitude doubles, the intensity becomes 4 times. Amplitude triples, intensity becomes 9 times. Okay, very, very important. Amplitude becomes 1/10, the intensity becomes 1/100th, which is 1 by 10 square. So that is the relationship between intensity and amplitude. So remember this, and the definition of intensity, which is how much energy is flowing per unit time, which is watts of energy, and per meter square, so per unit area. Okay, everybody clear? So what happens is, if you take a planar wavefront, tell me whatever energy is there here, 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 per unit time, per unit area, won't it be the same? Because that energy is still on that same plane area. It is not on a bigger or a smaller area. So you will notice that the intensity remains constant. Intensity remains constant, and it is independent of the distance. Independent, independent of basically the distance. This is very, very important. This is like electric field. Due to a charged sheet, the electric field is sigma by 2 epsilon, and it remains constant no matter how far you go from that plane sheet. So same way, intensity is also going to be a constant, guys. Keep this in mind. Okay, very, very important. But what happens due to a line charge and a point charge? It's very similar to electric field. If you take a point charge, what happens to the electric field? Inversely proportional to r square. Remember, kq by r square. Same thing happens here also. The intensity is inversely proportional to the distance that you are square, to the distance from the source square. Very important. Square of the distance proportional inversely. Okay. So for a point source, it is inversely proportional to the square of the distance. For a line source, it behaves like a line charge, how the electric field would behave. Try and recollect the formula. It used to be 1 by 2 pi epsilon naught lambda by r. So it was inversely proportional to r. Same thing happens here. You will notice that the intensity is inversely proportional to just the distance raised to 1, or basically just the distance. So you can see the formulas are very similar to electrostatics electric field. That's easy way to remember. So just a quick recap. Intensity of the light is how much energy flows per unit time per unit area, which is also proportional to the square of amplitude. So it's inversely proportional to the square of distance for point source, which generates spherical wavefronts. Inversely proportional to just distance for a linear source, which produces cylindrical wavefronts. And for plane source producing planar wavefronts, it remains constant and independent of the distance. Is this absolutely clear, everybody? Okay. I did not write JEE Mains, man. During my time, it was JEE screening. And the JEE Advanced was called JEE Mains, and it was not objective or computer. It was written, subjective, step marking was there. So I have written JEE very long time back. Looks like you are very new to the channel. That's why you're asking that question. Or else my students know that Shreyas Sir wrote the JEE exam almost 20 years back now. Okay. So let's do some questions coming up on your screen, and here it is. The light emerges of a convex lens when a source is placed at the focus. The shape of the wavefront of the light is interesting. Let's figure this out. So there is a convex lens given. Okay, let me show the principal axis, and the light emerges of a point source which is kept at the focus. So there is a source which is kept. This is your source which is kept at the focus. Now, if you concentrate on the ray diagram, that will be better. So the rays of light will just go like this, then like this, and like this. Any ray which passes through the focus after passing through the lens becomes parallel to the principal axis. Hence, the wavefronts that one would expect on the other side will be also like this. This will be the kind of wavefronts. So these wavefronts will obviously be going like this forward. So these are nothing but planar wavefronts. Planar wavefronts. Is that right? So option C should be the right one. Very good. Very good, Siva. Okay. Asmi, I will answer your question later on. Put it up in the comments. Okay. Okay. Very good, Ridan. Amazing. Kritish, don't disturb man like this asking random questions. Focus, bro. Focus. J is 1 month before. Okay, I will conduct a special time pass session, casual session. You can ask all questions. Okay, sir, where do you go for holiday? Sir, do you eat idli with sambar? Sir, do you eat vada with sambar? Sir, do you dip idli in sambar and eat it? Sir, do you use fork while eating idli? All kinds of stupid questions you can ask. Okay, we'll keep a separate session for all kinds of any question. You can ask question about somebody else also. Sir, NTR, is he going out with Samantha, sir? Please tell me, sir. Any kind of question you ask me, then I will answer. Okay. For now, today we'll focus on this. I know you guys are very interested in asking some random doubts. Okay. Having said that, here is the next question. Find the ratio of amplitudes at amplitudes of light at a distance of at a distance of r and 2r from a point source of light. That is the question. So let's try to figure this out. So we have a point source of light, and it is generating light rays in all possible directions, spherical wavefronts. And we are right now at two places. First time we are at a distance r. Second time we are at a distance of 2r. So first time we are at a distance of r, next time we are at a distance of 2r, and at both these places, what will be the amplitude of light? Let's think, why will amplitude be different? Maybe amplitude depends on intensity. Yes. So if intensity changes, amplitude will change. And I know for a fact intensity will change. So let me label these points now. Let me call this point number 1. Let me call this point number 2. So if I take the ratio of intensity at point 1 divided by intensity at point 2, then it will be nothing but inversely proportional to the distance. So it should be R1 over here, R2 over here, and square of it, because intensity is inversely proportional to the square of the distance. So what is R2? R2, the second point from this source is at a distance of 2r. R1 is this distance, which is just r. So square of it, r cancels, 2 square is 4. So this will be 4:1 is nothing but I1 divided by I2. But we all know intensity is proportional to square of the amplitude. So I1 by I2 should be A1 by A2 whole square. And the reason for that, intensity is proportional to square of the amplitude. So therefore, instead of I1 by I2, I can put A1 by A2 whole square is 4 by 1. Therefore, A1 by our A2 should be nothing but 2:1. That is the final answer. So the ratio of the amplitudes is 2:1. Is that clear, everyone? How to figure this out? Very good. Excellent. Awesome. 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 Excellent. Excellent. Okay, very good. Let's move now to the next part, and I'll just explain it to you that Huygens proved reflection and refraction using again his own theory. And although derivation is not important for JEE Mains, but it is there for your board examinations. So just go through it once. So what he says is that first, for proving reflection, he takes a mirror. This is that reflecting surface. And he then takes a light which is incident. The red one is that incident light falling on that reflecting surface. So what happens is, this light wavefront was here, then it goes here, then it goes here, then it goes here, then it starts interacting with the mirror. So this point on that mirror behaves like a secondary source. It emits a secondary wavefront here, not in the front, because it's a mirror, it reflects. So it will not create new wavefronts forward, rather it will create in the reverse direction because it should reflect light. Then this point will reach here, but this will create a new source and a new wavefront. Meanwhile, this wavefront would have grown in size. Then this point will reach here. It will create like a secondary source, creating secondary wavefront. And this wavefront, meanwhile, would have grown more, and this wavefront would have grown even more. So like that, what happens? Each point will start interacting with the matter of mirror. But the first point which will touch the mirror is this, then this, then this, then this, then this. Finally, this will interact with the mirror, producing a wavefront. Meanwhile, this point would have already interacted some time back. It will create a wavefront here. This would have reached here a long time back. It will create a much bigger wavefront. This point would have reached very long time back, would create even bigger wavefront. This point very long time back, the first point, in fact, it will create a wavefront like this. So if you see, you will see new wavefronts, and if you draw a tangent to them, you will get the reflected wave, and that reflected wave will now start going like this. So using this concept, he was able to prove angle of incidence is equal to angle of reflection. Are you able to visualize what I just explained in this particular theory? Yeah. So this wavefront slowly will reach here. One point will start acting like secondary sources. This was the oldest point, creating the oldest and the biggest wavefront. The newer wavefronts will be here. So if you draw common tangents to all of them, you will get the new reflected wavefront, which is CD. Is this clear, everyone? Okay, great, amazing. And then you also have law of refraction, very similar, but the interface which is there, where the incident ray will or incident wavefront will interact, that interface will propagate the light. It will continue that light in the same direction. So when These light rays, for example, incident, are going to come over here. This is your incident wavefront. This is your incident wavefront. The first point which will interact with the medium interface, one is air, one is water, one is water, one is diamond, one is a liquid, one is some other liquid. So this point will interact first, then this point will come here, then this point, then this point, and then this point. So this will be the last point. This will be the first point to interact. This first point will create a small wavefront. This will also create a wavefront, but meanwhile this wavefront would have grown in size. When this point reaches here, it will also create a wavefront, but this point would have already created a big wavefront, and this point would have created even a bigger wavefront. So eventually when this point reaches here and creates a wavefront, you will see much bigger wavefronts being created previously. That is what you will see. So if you draw a common tangent to all of them, you will see the refracted wavefront. So the refracted, not reflected, refracted light. But you will notice that this wavefront and this refracted wavefront are not parallel, because this new wavefront which is created, no, that will be smaller in size, because this might be a denser medium. So the light will travel here in all directions with lesser speed. So like over here, the wavefronts would be of larger radius, right? Here, the radius will be smaller than this radius, because it is created in a denser medium. So that is why you will see the light will bend and it will tilt and go inside the medium. How many of you are able to visualize this? How many of you are able to visualize this? Let me know. Yes. Perfect. Okay. So you should know this from board's perspective, not so much from JEE Mains perspective. Okay. From JEE Mains perspective, you should know that, okay, he was able to explain it. That's more than enough. Now let's talk about interference of light. And we'll be using that now for Young's double slit experiment and all of that, which is very, very important. Okay, very good. Amazing, guys. So let's start. What is the meaning of interference of light? So let me show that to you by a simple demonstration. Okay, just take these two water taps, and this water tap is turned on. It is dripping water, tap, 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 and wavefronts are being created on it. Okay, now imagine I turn this off. I will turn this off. Okay, now it is off. You, it is off. Now I turn on this. This will create its own wavefronts from a different point, and the wavefronts will again propagate in all the directions. These are two different sources. Now imagine I turn both of them together. Now both of them are creating their own wavefronts, and do you see now they are meeting? These wavefronts are meeting at different places. Like this wave would be going like this wave will be going like this. It is meeting here, 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 everywhere. So they are interfering with each other, and it creates a beautiful interference pattern that we will study. So interference is when two or more, this is just two, you can have 3, 400 waves also. So two or more waves come and meet, interact together, and they produce a resultant wave. So that is nothing but interference. This is there in your 11th standard. So I'll just put it up over here. So you might have a wave like this, you might have a wave like this, have a wave like this. So when you have two or more waves, and these waves, they all come and they will meeting at a point, meeting simultaneously, or meeting means it has to be simultaneous, meeting at a point in space. They will superimpose and they will create a new wave. They will superimpose. They superimpose. They will superimpose means this wave's effect is also there, this is also there. All of them are creating their and maintaining their own effects, and they're adding their effects all together. They superimpose and create a resultant wave. A resultant wave. It might have a new amplitude and all of that. So this entire phenomena is basically called interference. So this entire phenomenon is called as interference. The same thing can happen with sound also, can happen with light also, can happen with ripples of water, can happen with any goddamn thing. So interference is a very generic term, guys. It's not necessarily got to do with light. It's got to do with any kind of waves. Keep that in mind. Okay. Now, there are multiple kinds of interferences which can happen. So let me show it to you one by one. The first kind of interference which can happen is you have this wave coinciding with another wave like this. This had amplitude A1, this has amplitude A2, this has intensity I1, this has intensity I2. They both meet, they both meet together, they both meet together and they end up producing a big wave like this. They end up producing a big wave like this because their crests are meeting with their crest and their troughs are meeting with their trough. So trough and trough, big trough, crest and crest, big crest. So this kind of interference is then called as the constructive interference. This is called as constructive interference. This is called as constructive interference. You will see that there is another kind of interference which happens where you might have this particular wave meeting another wave. This has amplitude A1, intensity I1, amplitude A2, intensity I2. These both meet and they produce, because a crest is meeting the trough, this trough is meeting the crest, you might see a smaller wave like this. This kind of interference where opposites meet, that is called as destructive interference, where they are trying to destroy each other. So you will see a smaller wave coming out instead of a bigger wave. So what decides whether it is constructive or destructive is a concept called as path difference. This is very, very important. Imagine there is a Pandu and there is a Champa. There is a Pandu and there is a Champa. Both of them are starting from the same place, okay, and same road actually, but the road deviates like this for Pandu and Champa. Pandu takes another road and Champa is taking another road, and finally the roads will meet. So when they reach the intersection, Pandu decided, I will go like this. Pandu decided, I will go like this. Champa decided, I will go like this. Their speeds are same only. Pandu and Champa can run at the same speed, but they took different paths. So when they finally meet back again, do you think they will reach together? I don't think so. Champa has taken a longer road. So when Champa arrives over here, I feel Pandu would be already ahead. When Champa reaches here, Pandu will be already ahead because I can see Champa's road is little longer as compared to Pandu. So there is a difference between Pandu and Champa. Although they were together, there is a difference when they again came back because their path lengths were different, and that is exactly called as the path difference. This is called as path difference. This is called as path difference. So this path length might be L1, this path length might be L2. The path difference symbol is usually delta x, and that delta x is simply L1 minus L2, but I do not know who is big, who is small. So usually I'll put a modulus symbol over there. So that is the meaning of the term path difference. How many of you understood this concept? So whenever a thing starts simultaneously with other thing, but they take different paths due to some reason, and when they meet, they find themselves at different places. So that is then going to produce a path difference in them. Now, how does it happen in light? There are multiple reasons for it. One such example, let me show you. Imagine we have a glass slab. We have a glass slab, and let's say we have from the same source of light, from the same source of light, it is one ray is entering the glass slab, other ray is not passing through the glass slab. So this light ray, which is not passing through the glass slab, will be very fast and quick, whereas this light which enters the glass slab will be slower, because in the glass slab the speed reduces. So by the time it reaches here, this ray would have gone much ahead. And when finally it comes out, I'm pretty sure this would be much ahead of this ray would be much ahead of this particular ray. So although they both came from the same source, although they both came from the same source of light, this ray ended up being faster and it ended up becoming little ahead as compared to this ray which got trapped, which was slow and it fell behind. So because of that, 100% there was a path difference. You can see this is exactly the path difference between them. This is nothing but the path difference delta x between them. Can you see that how a path difference was created just by putting a glass slab? So some rays will not pass through it, which will be faster. Some rays will be slowed down. Can we find out this path difference? Can we find out this path difference? Yeah? Can we find out this path difference? Everybody understood this? Yeah, we'll come to phase difference also in a bit. Hold on. First, let me explain you path difference. Because these concepts, many teachers do not explain while teaching wave optics. And students keep thinking wave optics is very dangerous topic, sir. But I will explain everything. I know it is 11th standard concept, but still I have to teach you, no? Well, I cannot say, oh, you study there, here. I want to teach you everything. Okay. Okay, understood, perfect. So, Kritish, if you focus on the class rather than the questions, you will understand, bro. Okay, so these rays were till here in the same situation together. Only after this point, the difference happened. So, let's figure out how much time was spent in the slab. Time spent by, let me call this ray number 1, this is ray number 2. Time spent by ray number 1 in that particular slab. Let me assume the thickness of the slab to be T, refractive index to be mu. So time is nothing but the distance that you travel divided by the speed. Now the distance that you have traveled is basically the thickness T, or L also you can call it, because then that T and this T might look very similar. So I will use L then. So distance is L divided by speed of light, which I will put it as V. But I know the speed of light will no longer be V or same as outside. So I think I can use my Snell's law or ray optics concept and figure out how much that V will be. So the speed in a new medium, speed in any particular medium, remember, is speed of light divided by refractive index. Higher the refractive index, slower the speed it is. So C divided by mu is basically V. So instead of V, I can also put it as C divided by mu. So therefore, it will become L mu divided by C. That is the time spent. That is the time spent inside. Now, in that time, how much did the other ray go? So, in that time, the ray 2 traveled how much? The ray 2 traveled how much? Length 2 from here to here, whatever it traveled is length 2, and that length is nothing but speed multiplied by the time. Speed multiplied by time. This ray was outside, so it will travel with c speed only. The time will be exactly this. So it will be nothing but L times mu divided by c. C and c will cancel and you will be left with mu times of L. So the length 2 that it has traveled is mu times of L. So this ray, in that time which ray 1 was trapped, it has traveled mu times of L distance. So if this has traveled mu L, this has only traveled L, how much is that path difference now going to be? How much is that path difference going to be? It will be nothing but L2 minus that length over here. So it will be nothing but mu L minus L. So therefore L will be common into mu minus 1. So this is the path difference which is introduced because of a glass slab. The thickness of the slab into mu minus 1 is the difference of the path which is introduced because you put a glass slab in the way of the light. Did you now understand this derivation, guys? Everybody with me? Okay, very good. So tell me now, can you solve this particular question? Can you solve this particular question where I will keep two glass slabs? I will keep two glass slabs and let me see how many of you can figure it out. Two glass slabs of different lengths. Two glass slabs of different lengths. The light is entering both these slabs. Light is entering both these slabs like this. This slab has mu1 and thickness L1. This has mu2 and thickness L2. Both these light rays came from the same source. Okay, they came from the same source, bro. Okay, same source. Can you figure out how much is the path difference? Can you figure out how much is that particular path difference? This is the question. A very straightforward question in front of you. If you have one slab, the path difference created is L into mu minus 1. Now, if you have two glass slabs, what will be the path difference created? Okay, come on, think about it carefully. Okay, come on. Think what we should do. I will tell you one thing. Each ray will create a path difference if you compare it with some ideal ray which will not go through any of these. Let's take an ideal ray, let's say like this, which is neither going through the first one nor going through the second one. It is going, straight like this. Imagine. It is neither going through any of the slabs. So this ray with this ray will create a path difference 1 of, basically this will be behind of this by how much? Length 1 into mu1 minus 1. This is the difference between this ideal ray which is neither going through 1 or 2 glass slab, and if I compare both of them, this is behind by this by delta x1. Everybody agrees with this statement? Everybody agrees with this particular statement. So this particular ray was that ideal ray which would have gone really front. So if you ask me what is delta x1 is only this much, guys. This is delta x1. Similarly, this ideal ray with the second glass slab will have a path difference delta x2 of how much? L2 into mu2 minus 1. L2 into mu2 minus 1. Agree? So now the real question is, what is the difference between this ray and this ray which has gone through the glass slabs? That means I have to figure out how much is basically this one. That is my delta x. I think it is very obvious now. This is this minus this. This delta x is technically delta x1 minus delta x2, but I will have to take the mod of it because I do not know which one is bigger, which one is smaller. So that's all. I have figured it out. So this will be equal to mod of delta x1 is nothing but L1 into mu1 minus 1 minus L2 into mu2 minus 1 mod of it. So you can leave it like this, or if you want, you can just open up the brackets, but this is also good enough only. So that is the net path difference. Did you love the way we solved it? We introduced a new ray to solve the problem, which was not there originally. And then we compared this with that ideal ray, this with that again ideal ray. We founded out individual part differences and then subtracted them. Don't add them because this quantity is this whole thing minus this thing. So we wanted to figure out how much is this ray behind this or ahead of that. So we had to compare both of them. Okay, understood? Now you cannot forget this kind of concept. This lecture is going to be very long, bro. Yeah. Ha. Sabri, I knew a lot of people answer this and they have written this type of things. I have seen many people write L into mu2 minus mu1. Then my question is, what is L? Because L is not same, no? L1 and L2 is there. So which L will you use? So that is why it is not just modifying this formula into L into mu minus 1. That is wrong. So you have to use this. If L is same, then you can take L common and all of that. But still, it is this quantity, L into mu1 minus 1 minus L into again mu2 minus 1. Okay. So 2 times. Okay. All right. Perfect. Perfect. Now that you have understood what is the meaning of the quantity path difference, how to introduce it with a glass slab, there are multiple ways. In fact, the Young's double slit experiment does exactly that. It creates path difference. We'll come to it later on. Now, this path difference is what decides whether it is going to be constructive or destructive. Okay, constructive or destructive. So if you see, in case of constructive interference, you will notice that the path difference either will be 0, or it can be lambda, or it can be even 2 lambda, or in general any n times of lambda. Why I'm saying like that is because imagine this was a wave and the other wave is over here. You can see still constructive is happening because the trough crests are together, but exactly one wave behind you have the other wave. Exactly one wave behind you have the other wave. Still it will be constructive whenever they meet. So whether it is just one wavelength, or even if you shift this by one more wavelength, two wavelengths, three wavelengths, wherever they meet, some crest and trough will meet. That is why I'm saying whenever the path difference is any integral multiples of lambda, it will always produce constructive interference. Is this concept clear, guys? Why it is any n times of lambda? But for destructive interference, you will notice, imagine this is our wave. You wanted a trough. So basically like this. Now also destructive will happen. You can see the difference is lambda by 2 between these two waves. Lambda by 2, trough, crest, crest, trough, trough, crest, trough, like that. So when difference is lambda by 2, there is a destructive interference happening. Not just that, you can move it more. Okay, you can move it more also. Like for example, here. Now this is actually 3 lambda by 2, if you notice. Lambda by 2, lambda by 2, lambda by 2, 3 lambda by 2. Then also destructive will happen. So in fact, lambda by 2, 3 lambda by 2, 5 lambda by 2, all the odd multiples of lambda by 2 will create the destructive interference. So this part difference should be basically lambda by 2, 3 lambda by 2, in general 5 lambda by 2, and you can say odd times lambda divided by 2. Is this absolutely clear, my dear warriors? Yeah, very good. Excellent. Now, that's not all. That's not all. This amplitude which you get in this situation for constructive interference, the amplitude which you get for constructive interference will be A1 plus A2, because both the amplitudes, this and this, will add, Whereas in this case, the amplitude will be the difference of the two, but I do not know who is big, who is small. So it will be A1 minus A2. It will be A1 minus A2. Keep that in mind. If you talk about the intensity, in this case, the intensity will be maximum because constructive interference. And guess what? It will be root I1 plus root of I2 the whole square. Yeah, it's slightly strange, but that is the formula. The intensity over here when constructive interference happens is I1's root, I2's root added inside the whole square. And the same thing for destructive interference to produce that minimum intensity is root of I1 minus root of I2. Instead of plus, there is minus, and then you have whole square. Very important formulas, guys. So for constructive versus destructive, you should know all these things. What's the net amplitude? This is your net amplitude. Net amplitude. This is obviously also your net amplitude. Why I have put modulus? Because I don't know who is bigger, and amplitudes have to be always positive numbers. That's all. Yeah, perfect. Excellent. Now comes the last part of it, and that is called as the phase. That is called as the phase of it. See, if you take any wave, right? If you take any wave, when you take a wavelength, this is a wave length. It corresponds to one oscillation, or basically one period, one time period, one time period. And in circular motion terms, it is one rotation. It is basically corresponding to one rotation. One rotation. And one rotation in circular motion corresponds to 2 pi radians. 2 pi radians. So, any 2 points which are separated by a wavelength is basically one complete oscillation, one time period of a circular motion, and one rotation of a circular motion is 360 degrees or 2 pi radians. Now, you take any two random points which are separated by some delta x difference. Those two are, in circular terms, how different in angle? What is the difference in the angle, or what angle do they correspond to in the circular motion terms? Answer is simple. If lambda corresponds to 1 lambda corresponds to 2 pi radians, then delta x corresponds to how much? That angle is called as the difference of phase, or the phase difference is basically called as the phase difference. So what happens is, when you have one complete oscillation, it is 2 pi radians. But when it is half of it or 1/4 of it, it will not be one rotation. It might be pi by 2 radians, pi by 3 radians, 60 degrees, 30 degrees, 50 degrees, 120 degrees, whatever it is. So that angle which it corresponds to is called as the difference of phase, or phase difference. And we can find this out very easily by unitary method. This is to this is to how much? So this delta phi will be, you put delta x as it is, and answer should be in radians. So 2 pi will be on the top, the whole thing divided by lambda. So 2 pi by lambda into delta x will give me delta phi, which is the phase difference. Very important formula. Is this clear, everybody? Everybody, absolutely. So when you have two or more waves which are interfering, they will also create phase difference between them. So just imagine this. Just imagine, say for example, there is a wave like this, and I tell that there is another wave like this. Okay, and their path difference, I tell you, their path difference delta x comes out to be example lambda by 4. Then what is their phase difference going to be? So delta phi will be what? Think about it. 2 pi divided by lambda into delta x. Delta x is lambda by 4. So this will give me lambda cancels. 2 by 4 is 1 by 2. So pi by 2 radians. Pi by 2 radians. Now this kind of interference, delta x is neither a multiple of lambda nor an odd multiple of lambda by 2. Lambda by 2, 3 lambda by 2. No, it is neither odd nor just a simple multiple. So it is neither constructive nor destructive. It is intermediate interference. Intermediate interference. Intermediate interference. It is neither constructive nor is it destructive. It is something else only. If this was lambda by 2, 5 lambda by 2 or 3 lambda, 7 lambda, then it will be constructive or destructive. Now it is neither of them. So the phase difference between both of them in this situation came out to be pi by 2 radians. Same way you can find the phase difference in this case also. So you will notice if you put delta phi is equal to 2 pi by lambda into delta x formula, you will notice when you put 0, the phase difference will be 0. When you put lambda, check this out. Instead of delta x, if you put lambda will cancel. It will give me 2 pi. It will give me 2 pi. If you put 2 lambda in this formula, 2 lambda will cancel. 2 2s are 4. It will give me 4 pi. So it will give me 4 times of pi. Next will be 6 pi. Basically, I will get even pi or basically 2n pi. It's even number. It is always going to be even pi. So whenever the phase is 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, like that, even times of pi, it is regarding constructive interference to produce maximum intensity, maximum amplitude, okay, and they are said to be in phase. Such two waves are said to be in the phase. So when they are in the phase, meaning their phase is same, crest with crest, trough with trough, similar phase. That's why they are said to be in the phase. They produce constructive interference. But in this situation, notice what will happen. If you put lambda by 2, going back, lambda by 2 instead of delta x, lambda cancels, 2 cancels, pi will remain. If you put 3 lambda by 2, 2 cancels, lambda cancels, it will become 3 pi. 5 lambda by 2, 2 cancels, lambda cancels, 5 pi. Basically, you will get odd times of pi. So it will be either pi, then 3 pi, then 5 pi. In general, it will be an odd number times of pi. Such two waves are said to be out of phase, because the crest meets with the trough meets with the crest. They are out of sync. Okay, they are not in sync, they are out of sync. You can say out of phase, and that is why you will see they are going to produce destructive interference. Is that clear? Everybody with me on this? Very nice. Very nice. So let's see if you can solve few questions coming up on your screen. Two waves are meeting at a point and their wave equation is E naught sine omega t and E naught sine omega t plus pi by 3. Find the amplitude of the resultant wave. Okay, before going to this, one last thing of intermediate interference I had to give you. Where did it go? Intermediate interference. See guys, one interesting thing you will notice regarding in general interference, let's say even I call it intermediate interference. Try to see a relation between constructive and destructive. Try to see a relation between constructive and destructive. Things will start making sense. if I take the amplitude of the first wave as a vector quantity, let's say A1, the amplitude of the second wave also as a vector quantity, but in this angle, 0 degrees or 2 pi. 2 pi means same direction, 360 degrees. So if the second amplitude as a vector is in the same direction, as the first amplitude, because angle is 0 or 2 pi or 4 pi, 0, 2 pi, 4 pi means same direction. Then if you add both of them or take the vector addition of both of them, you will get the resultant vector like this. And that will be A1 plus A2. This looks like vector addition to me, because even in destructive interference, observe, if I take the first amplitude as a vector quantity, let's say A1, the second amplitude, if I treat it like a vector, but making an angle of pi radian. Pi radians means opposite, 180 degrees. So it is like this. So this is A2. If I add these two vectors, I am going to get this quantity, which is obviously A1 minus A2. This is obviously A1 minus A2. Oh, this tells me that actually I should treat amplitudes like vector quantities with the phase difference as the angle between those vectors. See how two different chapters get related suddenly. So, if I have in general two random waves and this has amplitude A1, this has amplitude A2, and there is a path difference between them. Which creates a phase difference delta phi given by 2 pi by lambda multiplied by delta x. It's like saying you take the first amplitude as a vector quantity, you take the second amplitude also as a vector quantity, but show it making an angle, of delta phi. This is very important. Show it making an angle of delta phi, which is the phase difference, and arrange those two vectors like that. Then the resultant vector which will be there, that resultant vector will be having the magnitude of the resultant amplitude. So whatever is the final amplitude, AR, will be given by the vector addition of these two amplitudes with the angle as the phase difference. This is a very, very interesting concept. So these two waves together are producing a new wave of a new amplitude given by the vector addition. Is this absolutely clear? Now we can use our vector knowledge and write it down very easily. So the resultant amplitude will be root of A1 square plus A2 square plus 2 times A1 A2, but here you will have cos delta phi. That's it. That is the answer. So that will give me the resultant amplitude. Same formula which was used in vector addition. Nothing different is. Okay. So I think we should obviously block this off for convenience. Even we can write down the resultant intensity of the new wave, but there is no square root and squares over there. Instead, what you get is the first intensity plus the second intensity plus 2 times root of I1, I2, 2 times root of I1, I2, and you will still have the term cos delta phi outside the root. Yeah, cos delta phi is outside the root, keep that in mind. So this is the resultant intensity formula which you get, and this comes because intensity is proportional to the square of the amplitude. Okay, I had given this to you before. So these formulas become the God formulas for interference, for any amplitudes, for any given intensities. So quick revision of what we learned in interference. Interference is nothing but the phenomena where two or more waves meet, superimpose, and produce a resultant wave. And that can be caused by path difference, like two waves entering through two different mediums or through different places, creating a path difference, like the one in the slab creates L into mu minus 1 path difference. And then we saw that the interference, which has some path difference, also creates a phase difference. It also has a phase difference given by this formula. And the resultant amplitude is given by simple vector addition of the amplitudes, taking the angle between the vectors as the phase difference angle is. Intensity, also a very similar looking formula. When the phase difference or path difference is 0, lambda, 2 lambda or 2 pi, 4 pi like that, it is constructive, amplitude and intensity is maximum. It is in phase. When they are opposite, amplitude and intensity are the least, and the path and the phase difference are lambda by 2 pi or 3 lambda by 2 3 pi, 5 lambda by 2 5 pi, basically odd lambda by 2 or odd pi. They are said to be out of phase or out of sync. Great. So it's time we solve now these questions coming up on your screen. Let's see if you can get it. Two plane polarized waves combine together and find the amplitude of the resultant wave. If you notice, both of them are signs, both of them are amplitude equations. So this pi by 3 is basically the phase difference. Phase difference over there. Both their amplitudes are E0 only. So if I want to find the resultant amplitude, it will be root of E0 square plus E0 square plus 2 times AB. That means E0 E0 cos delta phi. Delta phi means cos pi by 3. Okay. So E0 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 square is there everywhere. Under the root, it will just become E0. Whole thing under the root. 1 plus 1 plus 2 cos 60 is basically half. So it will become E0. 1 plus 1 plus 1 is basically root 3. So E0 root 3 will be the answer. But root 3 is nothing but 1.732. So approximately speaking, it should be option number A. Approximately speaking, it should be option number A. Got it? Very good. Yes, May. That is the correct answer. Yeah, this is the actual formula. Ken Karthik, correct? Yeah, this is how it is. Why can't we use triangle? We can use triangle also. See, triangle method or parallelogram method is just a method. It is not necessary that you have to only use parallelogram or triangle, anything like that. It's up to you which method you want to use. This is analytical formula. If you want to do it geometrically, you will do it by triangle or parallelogram or polygon method. Okay. Let's do another question coming up on your screen. And here it is. Actually, I'll do it here first and then we'll go to the next problem. If the amplitudes of two waves are A and 3A, find the ratio of maximum to minimum intensity of resultant wave. That is the question. Let's try to figure this out coming up on your screen. Okay. So maximum and minimum intensity will happen during constructive and destructive. That's obvious. Amplitude is given. We can also figure out how much the intensity will be. Well, if wave number 1 has an amplitude equal to A and wave number 2 has an amplitude of 3A, the intensity of wave number 1, if I assume it as I, think about it, the intensity of the other wave should be square of it. So it should be 9 times of I. The reason for that is intensity is proportional to the square of the amplitude. So the amplitude is triple, the intensity will be 9 times. That's very obvious. Okay. Now, let me figure out how much will be the maximum intensity. We just saw the formula of maximum intensity happens during constructive interference, this one, and destructive interference gives me least intensity. So let's use those formulas directly. So Imax will be root of I1 plus root of I2, which is basically 9I and whole square, and I minimum will be root of I minus root of 9I whole square. So if you do the math, it will be nothing but root of I. Root 9 is basically 3. So 3 root of I whole square. I plus 3 root I will be 4 root I. So 4 root of I whole square, which is 16 I. That is what it is. 16 I is the maximum intensity. Here, this will be root I minus 3 root I whole square. 1 minus 3 is minus 2. So minus 2 root of I and whole square. But minus 2 square will be 4. Negative square is positive. 4 times of I. So therefore, my maximum intensity by my minimum intensity will be 16 times of I divided by 4 times of I, which is 4:1, which is basically 4:1. That's the answer. Everyone clear about this? Very good. Excellent. Shall we do another question coming up on your screen? Here it is. Two waves have a path difference of lambda by 3 and intensities I and 4I. Find resultant intensity. Find resultant intensity. Very nice question. Let's try to solve this. Two waves which are interfering have a path difference of lambda by 3. Find their resultant intensity. Okay, let's think. If path difference is given, we can easily find the phase difference. What's the formula for phase difference? It is 2 pi divided by lambda multiplied by delta x. So 2 pi is as it is, lambda is also as it is. Path difference is given to be lambda by 3. So this will just become 2 pi by 3 radian, okay, or basically 120 degrees. Now use this for intensity. Resultant intensity formula, recollect, it was intensity 1 plus intensity 2 plus 2 root I1 I2 into cos delta phi. So first intensity is I, second intensity is 4I plus 2 root I into 4I into cos 120 degrees or 2 pi by 3 radian. So this will become I plus 4I is nothing but 5 times of I plus 2 into root 4 is 2, 2 2s are 4, so 4 times of I. Cos 120 is minus half. Cos 120 is minus half. So this will become 5I. 4 by 2 is 2. So minus 2I. So this will basically become 3 times of I. That is the answer. So 3I is the answer. Understood, guys? Clear about it? Pakka? Everybody? Very good. Very good. Excellent. Excellent. Amazing. A very similar question is there over here. This was asked in the year 2021. This was asked in the year 2021. Two light sources having intensity ratio 2:1 produce an interference pattern. The ratio of Imax minus Imin and Imax plus Imin. Will you be able to solve this? Because we just figured out a very similar question where I had given you amplitudes were in some ratio. What is Imax by Imin ratio? So it is a very similar question, guys. I will just give you the hint of this. The intensity ratio is 2:1. So I1, if you assume it as I, or basically, you can just take it as 2I. I2 is basically just I. So from this, try to figure out how much is I max. Try to figure out how much is I minimum. Remember, I max will be root of 2I plus root of I whole square. And this will be root of 2I minus root of I the whole square. Minimum will have minus, positive will be for plus. Then put all these values over here, you will get the answer. Okay, you will get the answer. But keep in mind, over here they have given that the ratio is 2x. Okay, 2x means basically this will be 2 2I or 2x into I. You can say 2x multiplied by I, and this will be just I. So the ratio is 2x. So over here also, when you substitute it accordingly only. So when you substitute, you will substitute it accordingly only, like root of 2xi plus root of I whole square, and this will be root of 2xi minus root of I whole square. Just do that, you will get the answer. Okay, so please try this question out as homework. I have given you the hint. Homework. Now you are seeing this word called as coherent. You might be wondering, what on earth is this meaning? So let me tell you, whatever formulas I gave you right over here, whatever formulas I gave you over here, and when we discussed all of this, all these were for coherent sources. This, all these were for coherent sources. So what is the meaning of that? What is the meaning of that? See, coherent source is basically predictable and they maintain phase difference. They maintain their phase difference, usually a dependent usually dependent sources, not a usually, they are dependent sources from the same primary source. What do I mean by all these things? Don't worry, I will explain. So what happens is, imagine you have a wave which is like this, the second wave which is like this. They have a phase difference, they have a phase path difference also, and that always continues. It's not like sometimes it is more, sometimes it is less. Even this, their wavelengths could, their amplitudes could be different, that's okay. But main thing is crest, crest, trough, trough should match. That is the most important thing. Okay, their crest, crest, trough should be matching. This also is coherent only. Although it is destructive, they are matching. Always I know it is predictable. If trough is coming now. Later on also, if a trough comes, trough is only coming. So it is predictable. And that happens from a single derived source. Meaning, imagine you had a source over here, that source is producing its wavefronts, and then somewhere in the front you have two slits or two obstructions like this, two gaps over here. These two gaps that you see, this gap and this gap, S1 and S2, they too now behave like two new sources. They too now behave like two new sources, something like this. And this S1 and S2 are basically the dependent sources from the same primary source. These two are always going to be coherent, meaning if this source stops, both of them will stop producing light. If this produces, the two sources will always receive the wavefront simultaneously, so they will behave in coherent manner. They are in sync. They are predictable. I know if this is getting crest, what is this getting? So they are predictable, they are derived, they are dependent. they depend on this, they are derived from this. So that is why they are coherent sources. So for coherent sources, you can use vector addition, vector addition, vector addition to find resultant, to find resultant. You can use vector addition to find the resultant. This is very, very important. Whatever we learned till now, it is only applicable for these kind of sources. So, sir, what is incoherent sources then? So, if a source is incoherent or not coherent, that means instead of maintaining the phase difference, their phase difference keeps changing, keeps changing. Usually, such sources which are independent sources usually are going to be incoherent sources. Meaning, there is one wave which is like this, another wave is like this, then break, then like this, and then like this. Sometimes the crests are matching, sometimes there is a break, and maybe something else is coming. So there is no guarantee what is going to come from the other side. It's like parts in bursts, waves are coming. Sometimes this wave is like this, and then this wave is like this. Wavelength is changing, frequency is changing. These are incoherent sources. Or, you know, something like this. This wave is coming continuously, papa, but the other wave is coming. Then suddenly it is in constructive. Then suddenly it comes, but in destructive, like this. Then again something happens to it. Again it becomes constructive. So there is no guarantee of what is going to happen. So that kind of behavior is incoherent source. Example of incoherent sources, just like we saw for coherent, where you have two independent bulbs. This is an independent bulb S1. This is another independent bulb S2. So maybe this is going to produce waves now, then it is not going to produce for some time, then again going to produce. Meanwhile, this had produced now, then after some time, then now again like this. So there is no guarantee that these two waves will be in sync. They are independent sources. And then when you see such kind of interference, so first of all, caution, caution, caution. What caution? Can't use vector addition. Can't use vector addition. Can't use vector addition for resultant. For resultant, this is very, very important. Rather, finding the resultant intensity becomes very straightforward, guys. So the intensity of the resultant wave is very, very simple. It is just going to be simple addition of all their intensities, I1 plus I2. How many ever waves are there? Just add both of them. So if there are two sources, so there will be two numbers only. So it is just I1 plus I2. There is no plus 2 root I1 I2 cos phi. Like over here, the resultant intensity was I1 plus I2 plus 2 root I1 I2 cos delta phi. There is no such term of cos delta phi because there is no constant phase difference. So that nullifies and you just get I1 plus I2. This is a very important formula. There were questions in the JEE Mains on this concept also. Okay, if it is incoherent sources, what happens? It's there in NCERT as a small line or a two lines, but this concept should be understood that okay, if it is incoherent, sometimes it is constructive, sometimes it is destructive. So the cos value will average out and become zero, because sometimes cos will be positive, sometimes cos will be negative. So it will keep on rapidly changing the nature of interference so fast that your eyes will not be able to even detect it. So you do not see the variations, fluctuations, and you will feel it is a constant intensity of just simple addition of intensities. Okay, very good, excellent. Now we'll start with Young's double slit experiment after the break. So we'll just have a break right now. Let's have a break for half an hour to 25 minutes. Okay. All right. We'll meet after the break, guys. Cool. Yeah. Because after the break, we'll do YDSC and then diffraction and polarization. It's going to be a long lecture, so be prepared. Have your dinner and come. Okay. Don't go anywhere. After the break, be back. See you. Take care. Welcome back, guys. Time is up. It's time to start. Yep, Young's double slit experiment. Let me know quickly in the chat box if I'm audible, visible to all of you. Yes, it's time to start YDSC. Yep. Get back, everyone. The break time is over. Let's start. Excellent day. Excellent day. All right, Deadly Gaming. I will ask Diksha ma'am. Yeah. So, before the break, we just spoke about interference, and we saw that in case of interference, you have two or more waves meeting, creating a resultant wave, and we saw what the difference in the path is called path difference. The phase is different, so phase difference, which is related to the path difference, amplitude using vectors, and same way you can find the resultant intensity. That was true for coherent sources, which I told are derived sources or dependent sources from the same source, where the phase difference is constant. But the moment it is not, it is incoherent, and then you cannot use the regular formulas. You just have to simply add their intensities. As simple as that. Now, in order to observe interference, there are many arrangements possible. One of the most popular one is the experiment performed by Thomas Young, and it is famously called Young's double slit experiment, because in that experiment you have two slits, you have a screen in a dark room, and you observe the pattern in that dark room on that screen when the light passes through those two slits, and a beautiful pattern appears. That is what this setup is all about. Short form YDSE, Young's double slit experiment, YDSE. Okay. So, based on that particular setup, we are going to study what exactly happens, what are the modifications, what does it depend on, so what kind of nature of interference and all of that in this particular setup. So, what happens is you have a singular light source, as you can see over here. Observe it carefully, guys. Okay. So, you have basically a simple light source over here. That light source will emit waves in all the directions, and those wavefronts will slowly grow and move ahead. They will move ahead. Eventually, they will encounter two slits in an opaque sheet or an opaque wall. These slits are very thin or narrow. So, these two slits, which have light falling onto them, are dependent on this source. So they are derived sources, and hence they are also coherent in nature. So I know if this particular slit is producing this wave, this slit is also producing a similar kind of wave and maintaining that phase difference. So the outcome becomes predictable rather than being random and unpredictable. Now, these two slits, they themselves act like new sources. So, these two will start producing wavefronts like this. And these wavefronts will propagate in all the directions around that space. There is a screen in front. There is a screen in front. And on that, you can see how the waves are meeting. Like it might happen, some wave from source 1 and some wave from source 2 is meeting at the point, but maybe they are meeting constructively. So then you will see a bright region over here. Maybe that same source generating that wave and the source 2 generating another wave meeting here might meet destructively. So you might see a dark region over here, because constructive means intensity will be more, destructive means intensity will be less, and they cancel up and gives you very little light, which is like dark region. Because this setup is conducted in a dark space, so it will appear dark. So wherever the light rays meet to produce constructive interference, that space will be bright. Wherever they meet to produce destructive interference, that space will be dark. And that is why you will start seeing a kind of a pattern on the screen. Let's have a look at the simulation. Yeah, let's have a look at the simulation to understand it. But I'll give you a hint. If you concentrate at a point which is directly on the perpendicular bisector of those slits, which is on the perpendicular bisector of those slits, okay, and on the screen, you will notice the wave which comes from source 1 and the wave which comes from source number 2, they both travel same distance to meet here. So there is no path difference when the waves meet at this point. There is no path difference when the waves meet at this point. That means they are in phase, they are in sync, no path difference, no phase difference. So 100% at this place, there must be constructive interference. That means this point will have to be bright. And once I know it is bright, I know this will be bright, this will be very large in intensity. Around that place, there will be a dark region. There will be a dark region. This much, at least, if you understand, now that simulation will make sense. So let's have a look at that simulation. But remember, we'll not use water now, we'll use light. So this is light, okay? And notice this is a light source producing light waves. This is another light source producing another light waves. Can you see beautifully how they are interfering with each other? And some places they are interfering constructively. That's why you see big bumps in that surface. Some places there is no variation, so it is flat. There is no variation here or here or even here. That's why it is flat. So this is destructive. This is constructive because here the bumps are there, waviness is there. Where there is no waviness, it is flat, it is destroying each other. So let's put it into action with the help of slits. So let's use double slit, not one slit. I want two slits, and slit width is very small. Okay, we can move it here and there. All right. Okay, slit separation also I can change however I want. Great. And I want to do it with light basically. So light, two slits, width is very small. Slit separation also I can change. I'll put it over here. Now see, I'll turn on the light and observe some kind of interference. So light wavefronts went. These two acted like new two sources, secondary sources generating new wavefronts. And you are seeing an interference over here. So I need a screen, and look at this screen. I will turn off the light for a moment so that you can see it clearly. Observe it. Can you see exactly in the front, there is a bright region which is formed. This is a constructive interference point. Then there is a dark region you can see because there is no variation in the light amplitude. So this is destructive interference. There is a dark region over here. Above that, again, there is a bright region because the waves are interfering constructively, then dark and bright. If I change the slit width, you can see how things change. You can see how things change. Slit width, okay? See, I've changed the separation between the two slits. Now they are far away. You can see the pattern will change. If I bring them close, again the pattern will change. The pattern has changed quickly. And you can see now the fringes have also increased. The fringes have also changed. I can again change it over here. I can use different color if you want. Okay, I will use orange color. I can use red color. Accordingly, the fringe width, the fringes spacing, everything will change. Yeah. So you can see alternate. This is a bright fringe exactly in the front. It's very faint, so little difficult to see, but I hope you're able to visualize it. I will use some different color maybe. Yeah, see blue color also. Blue color also. You can see that. Yeah, blue color also. You can see bright, dark, bright, dark. How many of you are able to see this? How many of you are able to see this? Can you see the fringe interference pattern? If I change the color, it will be different. Instead of blue, if I use red, the fringes will be different at different places. If I change this also, it will be different, guys. If I change this also, it will be different. You will see. Yeah. Now the fringes will be different. You can see alternate bright, dark fringes are being formed on it. You can also plot the intensity, how the intensity will look like. how the waves are going, everything. You can just have a look at it. You can play around with this simulation on your own also using FET simulator. Okay, so that is basically Young's double slit experiment. I think for the first time, most likely for most of you would have seen YDSC in action. Till now, you have just seen maths or just basic diagrams. This is how it looks like. So you have two slits from a single source, and those two slits allow the light to pass, and you will see beautiful bright and dark fringes. These fringes were not possible if light were particle, because if light was particle, then light would have just gone through the slits and you should just see two bright regions in front of the slits. But that is not what you see. Those two slits act like new sources producing new wavefronts, creating interference pattern rather than just allowing the light to pass straight. So it's not like the light just goes here and you see two bright spots here. No, the light will spread over here, creating interference, and that is the reason for observing it. Certain conditions are there, like the light should be monochromatic. Mono means single color. It should not be like some mixed colors are there, then you will not see the interference clearly. Sources must be coherent, that is natural, because if this source is independent of this is producing crest, this is producing trough, then it is trough, this is crest, there is no guarantee what will happen. You will not see any interference only. The width of the slit is comparable to the wavelength, meaning this slit that you see should be of the order of the wavelength, else you will not see the light spreading out. That is a concept of diffraction. Okay, so the light wavelength should be of the same size of the slit width, then you will see the light will spread, else the spreading won't happen too much. You want the light to spread in all the directions, so that is why this condition is essential. The waves from S1, S2 will interfere and obtain different patterns on the screen depending on the distance of the screen from the slits. Also, it depends on distance between the slits. It also depends on the wavelength of light. So, lambda, capital D, screen to slit, and small d, which is slit to slit. All three parameters decide how many fringes, where, what is the width, difference between the fringes. All these things depend on d, lambda, and small d. Small d is distance between the two slits. Okay? All right. The class will end around 10, 11 o'clock easily. Yeah. Okay. Perfect. Now, in order to find what kind of interference pattern will form, you take any random point on the screen. Let's say random point P. It is having some y coordinate from the central location. This point is directly in front of the midpoint of S1, S2. The distance between screen and slits is capital D. Distance between the slits itself is small d. The source is producing a light of wavelength lambda. This light, when it reaches S1, will go in all the possible directions. This light will also move in all possible directions. Out of all the light rays, you are considering two light rays which are meeting at point P, which is at a distance of y from this point. Now, as you can notice, the ray from S1 is traveling less distance, whereas ray from number 2 is traveling more distance. So, ray number 2 has some extra path which is involved, creating that path difference. Which means by the time the ray from 1 reaches over here, ray from 2 is slightly behind, and that difference is basically your path difference. So ray number 2 is slightly behind ray number 1 by an amount of delta x. Is this concept clear? So that delta x is nothing but that delta x, which is there, is nothing but you take this distance and you take this distance, you subtract the two. X plus delta x minus x, that is nothing but the path difference. I hope this is absolutely clear in your head. The path difference between the two rays meeting at any random point is the bigger path length minus the smaller path length whatever is the difference is the path difference of those two waves causing that interference. Okay. Now, using analysis, geometry, Pythagoras, whatever you can say, all right, you will notice that this delta x, which is there, comes out to be yd by d, yd by d. Now, what is this y? This is that y coordinate. Capital D is the distance of the screen. Small d is the distance between the slits. How it comes is using Pythagoras. I'll tell you how. If you notice, this S1P is hypotenuse of this triangle, is hypotenuse of this triangle. Similarly, this S2P is hypotenuse of this triangle. So you have to use Pythagoras two times, one for a triangle, other one for this triangle. So S2P will be this, S1P will be this, and you have to use binomial approximation and all of that. And after that, you get this answer. Don't go so much into the derivation, but I'm telling you the method for that. What happens is it comes out as yd by d, which actually, I think I have it on the next slide. No. Okay. Not an issue. Notice one thing. What is this y small d by d? Well, see guys, if you notice, this is y, this is d, and if you draw this particular line and the angle between them is theta, y by d is nothing but tan theta. So technically, this is nothing but tan of theta, tan of theta multiplied by small d. Y by d, y by d is nothing but tan theta. Can you see that, guys? Everyone over here, very, very important. Okay, so this particular angle is theta. This is the d. This is 90 degrees, and this is nothing but your y. But usually theta is very small. When theta is very small, you know what happens? This hypotenuse also approximately becomes d only. It is slightly more than d, but almost d. So tan theta becomes sine theta. So sine theta is y by d. So this also approximately becomes sine theta multiplied by d. Sine theta multiplied by d. So basically, if theta is the angular position of that point, meaning with respect to with respect to with respect to the central point, where am I exactly? That is theta. That is the angle wise position. Then the path difference is small d into sine theta. But sine theta is tan theta, and tan theta is opposite side by adjacent side. So very easy to remember this. The same thing is there on the next slide also. The path difference is small d sine theta. The path difference is basically small d sine theta. Very straightforward. Hi Vanshi. Okay. Hi Sarang. Hello Divyanshi. Everyone. Perfecto. Sabrinathan. Alanch. Kar. Abhishek. Tanuja. Sine. All right. Okay. Don't go so much into derivations like I'm saying. Yeah. Just remember what it is. Small angles are there usually. Also, this distance is much, much larger than this. Okay, it is always the case. Your distance will be very large. The distance between the slits will be very less. This will be in millimeters. This will be in meters. So meters is more than millimeters. And the angle that you are seeing will also be small. Why is that angle small? Also, I'll tell you. Because when you go far away, the fringes will become very distorted, less bright, and they will not be clearly seen. In fact, even in a small region only, you might see hundreds and thousands of fringes. So you are generally interested in fourth fringe, fifth fringe, 10th fringe. You are not interested in 15,000, 25th fringe. No. So that's why you do not go very far away. And that's why the angle that is considered is also very, very small. So you should know all these reasons. Good evening, Gal, Bharat. Okay. Now, once you have understood, okay, sir, this is the part difference, which is small d into sine theta. Theta is the angular position. Guess what? I have already told you this. When you go to the central point, both the rays meet at the same time, same distance. So 100% constructively, they will interfere at C. So I'll get a bright region at C. But as I go away, I will see that bright will become dark, again bright, again dark, and again bright. So I will see alternating bright and dark fringes with a central bright fringe. With a central bright fringe. Keep that in mind. With a central bright fringe. Now, I am interested, sir, tell me what is it for constructive interference and what is it for destructive interference. Although there are formulas right over here along with fringe width, I will put it to you in a very simple way so that you are not bombarded with too much of information. See guys, I'll tell you in a very simple way. This is our screen. This is the distance between the screen and the slits. The two slits are over here. The two slits are over here. So this is small d. This is S1. This is S2. This is the central point C, central maxima. Okay. Then we said we take a random point anywhere. That is going to be theta, angular position. That will be Y. And this is obviously your D. Okay. Simple arrangement I have shown. This line is the screen. These are the slits and all of that. We know delta X is always going to be, part difference is always going to be D times of sine theta. Just imagine I want to locate bright regions. So if I want to locate bright regions meaning constructive interference, remember what is the condition for constructive interference? Try to recollect delta X. Yes, delta X will be n times of lambda. 1 lambda, 2 lambda, 3 lambda, 5 lambda, like that, starting from 0. So, which means n times of lambda, is d times of sine theta, but d sine theta is also d tan theta. Therefore, tan theta being y divided by d, this is what I will get, which is n times of lambda. Therefore, y will be n times of lambda capital D divided by small d. This is giving me y coordinate of any nth fringe from the central maxima. Y coordinate of the any nth fringe, bright fringe from the central maxima. So simple it is. Same logic, if you apply it, same logic, if you sit and apply it for dark fringe. So for dark fringe, you should get destructive interference. So since delta x is d sine theta always, this delta x will be odd times lambda by 2. Remember that? Lambda by 2, 3 lambda by 2, 5 lambda by 2. This is d only, but d sine theta can be written down as d tan theta. Tan theta is nothing but opposite side by adjacent side. That's going to be odd times lambda by 2. Rearrange it, you will get y is equal to odd number into lambda capital D by small d, and that 2 will remain over here. So the y coordinate of any dark or destructive fringe will be odd by 2 lambda d by d. This is very important. Why am I putting as odd number? Whereas in the printed material, most of the places, it will be n 2n plus 1 by 2 or n plus half and all of that. I really am not a fan of this way of writing it. I'll tell you a simple reason, because I will only get confused which fringe am I talking about. First fringe, second fringe, sir, n will be starting from 0 or will it start from 1? Sir, was it 2n plus 1 or 2n minus 1? Because both 2n minus 1 and 2n plus 1 are odd numbers. So it becomes very confusing. Rather place it as odd number. It becomes much simpler. So I'll tell you how the nomenclature works. how the naming works in this. So if you have the screen over here, this is our screen. At the center, first, you will have the central maxima. You will have exactly at the center. Okay, I'll use this. You will have you will have central maxima in the center, then some space, and then you will have the next bright fringes. So this is at C. So this is your central maxima, also called as the 0th maxima. Very, very important, because if you see the formula for maxima, y is n lambda d by d. The y coordinate at the center will be 0. So n, that number, will also be 0. Check it out. When you reach over here, y coordinate will be 0, n has to be 0. So because of that, it is called as 0th maxima. Getting my point? The immediate adjacent ones will be then called as first maxima. This is also first maxima. Then the next thing will happen. Second maxima, third maxima, fourth maxima, like that. So this is how you locate those maximas. This is how you will locate those maximas. Starts from the 0th and then it keeps on going. This number 0 also has another significance because 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 at C, delta x is 0. So because the path difference is 0, that is another main reason why it is also called as 0th maxima. That is why it is also called as 0th maxima. Now, you might be wondering, sir, will there be a 0th minima? Think carefully and tell me, will there be 0th minima? Answer is no, because all these dark regions are minimas, and at this point, you will not see the rays arriving simultaneously. There will be a path difference for sure. So that 0 number is a privilege given only to that point where the waves arrive together, not otherwise. So this one starts with first minima, because that is the first number that you will get. 0 is the privilege of only that place where the rays arrive simultaneously, like the one over here. Here, only at the center. So this is also going to have 0th order of interference. Whether it is destructive, constructive, doesn't matter. That number will be 0. 0th order of interference. Very, very important. Only because they reach here. Any other place, they will not be together. There will be some path difference. So it will start with 1, 2, 3 like that only. So this will be the first minima. Same first minima will be over here. First minima over here. This will be second minima. Then this is called third minima. You can also call it as third dark fringe. It's up to you. I can call it maxima minima also. This will be second minima. And then this will be third minima. Then you will get third maxima, then fourth minima, and it will keep on continuing. It will keep on continuing. Is this clear, everyone? Is this clear? So only the privilege is there with 0 at maxima at the center, because the path difference is 0. But for the minima, the rays don't arrive simultaneously. So we start with the number 1. Okay. If you ask me what is the value of n, or what is the value of path difference at the central maxima, think logically at the central maxima. at the central maxima, the path difference will be 0. The next maxima, it will be 1 lambda. Next maxima, that n will become 2. Next will become 3, and so on and so forth. So the path difference over here will be 0 times of lambda, which is 0. The path difference here will be 1 lambda. The path difference here will be 2 lambda, and so on and so forth. Here also, delta x will be 1 lambda. Delta x will be 2 lambda, 3 lambda, 4 lambda. That's how the path difference will keep changing. Whereas for minima, what is the path difference? For minima, what is the path difference? Odd lambda by 2. And where do odd numbers start from? Obviously 1, not 0, right? So the first odd number will be 1 lambda by 2. So notice the first path difference over here will be delta x, which is 1 times lambda by 2, or just lambda by 2. So it will be just lambda by 2. Next one will be second odd number is 3. So 3 lambda by 2. Next one will be 5 lambda by 2. Same thing over here. Delta x will be 3 lambda by 2. Here delta x will be 5 times lambda by 2, and so on and so forth. So whenever you have interference pattern, all these things are happening. Now don't remember these numbers. This has to come naturally. Do this exercise multiple times with your own hand in a rough sheet. Take a sheet, draw this. What is first maxima, second maxima? Why it is 0? Why it is not 1? Why it is 1 for minima? What is the path difference? Try it multiple times. This has to be in your head, because questions will directly tell the fifth maxima from the second minima is at so and so distance. So like that, questions will be there. So you cannot sit and think what is maxima, what is second minima. Like that, if you think, you will be gone. Waste of time. This numbering is clear. Is the numbering clear? How the maxima minimas happen and how these path differences are? Remember, for constructive interference, it is always integral multiples of lambda, all the green ones. For destructive interference, it is odd multiples of lambda, starting with 1 lambda by 2. Okay, odd multiples of lambda by 2. Sorry. Yeah. Okay. I'm so glad you are understanding everything, Athurva. And I really hope that you continue doing so in the days to come as well. Okay, awesome, awesome, crystal clear. Now, many people often wonder, sir, how many maximas and minimas will be there? What do you think? Answer is infinity or some finite number? How many maximas? Like second, third, fourth, fifth, 10,000, 20,000, 1 lakh, infinity. What do you think? This will keep on continuing? Well, let me tell you a simple logic for that. See, if you are at the central maxima, we saw delta x will be 0. When you go at some place randomly, delta x is not 0, rather delta x is equal to d sine theta. Now you keep on going at a very far away place, like this, imagine, at infinity. So you have finally reached very far away place, that is at infinity. What do you think will happen at infinity? This is very interesting. So this ray will almost travel like this, and this ray will almost travel like this. I have a feeling both of them will reach almost together when they reach infinity. Not together, sorry, a difference of d will be there. So notice this ray and this ray will almost become parallel to each other, and the path difference will almost become how much? Sine theta can't go more than 1, right? Theta will become 90 almost. And you will see that delta x delta x will not become equal to, rather it will become tending to d. It will not be equal to, but it is not equal to d. Tending means that only. It is not equal to, it is less than. So my delta x value in general, in general, in general is more than and equal to 0, but it is always less than d. This is very important to figure out how many fringes are being formed. This is very important to figure out how many fringes are being formed. Yeah. You're like, sir, how will this help me? Are you serious? I thought there is some crazy formula. No, it is just this formula, guys. This formula is enough to figure out how many fringes are formed. I'll explain. Well, observe now carefully. Say, I tell you, my distance between the slits is, example, uh, let's say 8 times of lambda. 8 times of lambda. That's all is given to me. Nothing else is given. Question is, how many fringes will be there? How many fringes will be there on the screen? Okay, that's the question. Let's try to figure it out. Now, if you take the screen, if you take the screen, okay, this is the screen example. The central maxima will obviously be 0 lambda. We'll just take on one side, then we know what will happen on the other side. 0 lambda. You'll also get a point with 1 lambda part difference. You'll also get 2 lambda. You'll also get 3 lambda. You'll also get 4 lambda. You'll also get 5 lambda. You'll also get 6 lambda. 6 lambda. You'll also get 7 lambda. But you will never ever get 8 lambda, because remember, my part difference has to be lesser than d, can't be equal to d. And my d itself is 8 lambda. So my path difference can at most be d less than that, get close to d, not equal to d. So it can never be 8 lambda. Do you guys agree with this? Same thing also continues on the other side. 1 lambda like that till obviously 7 lambda. It cannot be. So delta x has to be lesser than d. So delta x has to be lesser than 8 lambda. It can't be 8 lambda for constructive. Same thing for destructive also. So in between them, you are going to get 0.5 lambda by 2 is 0.5 lambda. 3 by 2 lambda is 1.5 lambda. 5 by 2 lambda is 2.5 lambda. You are going to get 3.5 lambda. You are going to get 4.5 lambda. Then you are going to get 5.5 lambda. You are also going to get 6.5 lambda. You will also get 7.5 lambda, but you can't get 8.5 lambda because delta x has to be less than 8 lambda, whatever you say. Same thing will continue on the other side, starting off with 5 lambda, and this will go on till basically 7.5 lambda. This is all the fringes that you are going to see. And yes, it is a large number, but it is not infinite. You can't go beyond that. That's enough for me now to figure out how many fringes are there. So count the number of dark fringes. Dark fringes, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 this side, 8 this side. So it will be 8 plus 8 on either side. It will be 16. Now let's count the number of bright fringes which will be there. Number of bright fringes. 1, 2, 3, 4, 5, 6, 7. 7 on this side and the central 0. So 7 on one side, 7 on the other side, and the central one. So 14 plus 1, that is 15. So 15 bright fringes and 16 dark fringes. That's how simple this question is. How many of you understood the technique of finding out the number of fringes using this method? So this inequality is very important. It's not like you have to remember it, but remember at the center it is 0. Towards the end, it tends towards the distance between the slits. So as you go far away, the path difference increases, becomes very close to the slit width, slit distances. Now just think about how many fringes can come in between and you are done and sorted with the problem. Okay, we can do one more question just so that you have full confidence. Imagine the wavelength is 0.2 millimeters and the distance between the slits, the distance between the slits is example 1.2 millimeters. 1.2 millimeters. Okay, this is the thing. Question is, how many fringes will be there? How many fringes will be there? That's the question. Okay, let's quickly do this, guys. First thing first, D is 1.2 lambda. So D is 1.2 millimeters. So 1.2 is how many times of 0.2? Just think about it. How many times? What is this number going to be? Yeah, guys, 0.2 into 6. Is that right? So can I say D is 6 times of lambda? That's it. This is the first thing which I will do. How many times D is of lambda? How many times D is of lambda? Now it is straightforward. Think in a very simple way. You will start with 0 lambda. For the bright fringes, 1 lambda. You can go at max till 5 lambda, but you can never be 6 lambda. Same thing on this side also, 1 lambda, and you will go till maximum 5 lambda. For dark fringes, you will start with 0.5 lambda, 1.5 lambda. You can go till 5.5 lambda. Same thing here. You will start with 0.5 lambda, 1.5 lambda, and all of that. You can go till 5.5 lambda. You can't go beyond 6 times of lambda. That's it. So now let's figure out how many dark fringes are there. So if you notice carefully, 0, 1, 2, 3, 4, 5 is 6 numbers up and 6 numbers down. So 12 dark fringes are there. If you ask me how many bright fringes are there, I will just say, well. So 1, 2, 3, 4, 5, 10. So 5 plus 5. And the central one, do not forget it. So don't put 0 actually, it is 1. So it is basically 11 bright fringes. I think after this, you will never ever complain of finding the number of fringes. This is also a common question. Okay, got it? Simple technique. Sir, can I also solve questions where I have to find where is the bright fringe, where is the dark fringe and all of that? Yes, man, I will show you that also, that kind of question also. Say for example, it is given to me that capital D is 2 meters, small d is let's say 4 millimeters. Let's say lambda is given to be example maybe 800 nanometers. Can you find the second maxima and the third minima location y coordinate? Okay, what is the second maxima and third minima y coordinate? That is the question. All right, so let us remove this. Okay, let's think about whatever is given to me and what will be the condition for maxima and minima. So when we talk about the first part, which is the second maxima, in order to find second maxima, for maxima, the y coordinate has to be found using this formula, n lambda d by d. That's all. N times lambda d divided by d. So the y coordinate will be n lambda capital D divided by D. N is nothing but 2. Lambda is 800 nano. So 800 into 10 to the power minus 9. Capital D is 2 meters divided by 4 millimeters. So 4 into 10 to the power negative 3. Okay. 4, 2 cancels. 800 into 10 to the power 9 will become 10 to the power minus 7. And 1, 10 to the power minus 3 will remain. So this will become 8 into 10 to the power. This will become minus 4, I believe. But if you want, you can also write it as 80 into 10 to the power minus 3 meters, which is basically 80 millimeters. So at 80 millimeters, you are going to get our second maxima. Second maxima. Next part of the question says, find where the third minima will occur. Okay. In order to find the third minima, the formula used is slightly different. Remember, the concept is odd multiple of lambda by 2. The concept is odd multiple of lambda d by 2d basically. So use that formula. So it looks very similar to this, just that instead of n, you are going to put odd number divided by 2. Rest of the things is as it is. Okay. I'll just put divided by 2. Lambda is still 800 nano means minus 9. Distance is 2. Distance between the slits is 4 millimeters. So 4 into 10 to the power negative 3. Only thing is odd number. What are you going to put the odd number as? Come on, quickly think and tell me. Yeah, I know many people are going to say, sir, put the number 3. I knew it. That is why I'm doing this question. See, guys, I'll tell you what. See, for maxima, right? This is, let's say, 0. For maxima, we were talking about second maxima. So yes, it is 1 lambda. This is 2 lambda. So this is first maxima. This is second maxima. This is 0th maxima. For minima, be careful. This is 1 lambda by 2. This is 3 lambda by 2. This is 5 lambda by 2. This is first minima, second minima, third minima. So the third minima is actually the third odd number. So the third odd number, which is it? Is it 3? It is the second odd number 3. Third odd number is 5. So hence the number 5 will come over here. This is the common mistake which kids do. Now if you use 2n plus 1, 2n minus 1, still that confusion remains. Sir, will n start from 0 or 1? Is it 2n minus 1 or 2n plus 1? I get confused. So better to keep it simple. If you draw a simple diagram like this also, it becomes very obvious. Got it? Understood? Yeah. How? Oh, sorry. Did I put 80? My bad. It should be 0.8. No, why did I put 80? Sometimes this happens, guys. Okay. This should be 0.8 into, sorry guys, 10 to the power minus 3. This will be in meters. So this will be 0.8 millimeters. Thank you so much for pointing it out. Okay, coming back. So this will become 2 cancels. 8 and 4 also cancels, becomes 2. 2 into 5 will become 10. Understood? 2 and 2 cancelled. 8 by 4 is 2. 2 5s are 10. You have 2 more zeros. You have 10 to the power minus 9 and you also have 10 to the power minus 3. So what will happen? This will become minus 6. This will become 10 to the power 3 and this will become 10 to the power minus 6. So this will become 10 to the power minus 3 meters, which is 1 millimeter. 1 millimeter. That's the answer. Why can't we go by for 6 lambda in the previous question? In the previous question, where is that? This one. My D is 6 lambda. Remember, no matter what you do, my path difference always has to be less than D and it should be more than or equal to 0. So less than D means less than 6 lambda. So even 5.9 lambda will do, but 5.99 lambda will also do, but path difference can never be exactly equal to D, which is 6 lambda. And the reason for that, I already mentioned here, when you go really, really far away, what happens is those light rays from those two sources will almost be like this, parallel, and you are reaching basically at infinity, and our sources are barely over here, and their separation is basically D, almost parallel. So they are almost tending towards D, but not equal to D. Making sense now? Okay, perfecto. So that is why that is not taken. So this concept is very important, that even if you miss one number, no, you're going to get negative marks. And I don't want you to lose those marks because you made a counting mistake because of some conceptual error. So this inequality is very important for you to solve the questions. All right. Hello, Naveen. Is this all clear, guys, till this point? Let me know quickly in the chat box. Now that we have understood these concepts of maxima and minima, part difference, and all of this, okay, now let us go to the concept of fringe width. See, guys, you can see from one bright to next bright, or one dark to one dark, there is a distance between them. That distance is called as fringe width, nothing more. So fringe width is basically, fringe width is nothing but from one maxima to next maxima, or from one minima to next minima, what is the distance? You can easily get it from these formulas. This formula which is there, right? If you put n as n plus 1 and n, the difference between the two y's will be the fringe width. Think about it. Yeah. If you ask me what is going to be my fringe width, the symbol for that is beta, and that will be basically y n plus 1 minus yn. Reason for that? It's nothing but you have that screen, you have your nth fringe over here, nth fringe. This will be n plus 1th fringe, next immediate. In between that, there is only one dark. So that separation between them, that is basically called as the fringe width. So maybe this is my central maxima. This is my central maxima. So this minus this, whatever is left over, this minus this, whatever is left over is the fringe width. Between bright and dark, it is exactly the same. So if you notice, it will be n plus 1 lambda capital D by D minus n lambda capital D by D. N will cancel, and you'll be left with lambda capital D by small d. That is your fringe width. Is this clear? That is your fringe width. Last thing over here is, if you go from the center and see, if you go from the center and see how much angle does that fringe subtend, how much angle does that particular fringe subtend, that is called angular fringe width. That is basically how much angle does your fringe subtend. That is called angular fringe width, and it is not that difficult to find because this is almost like the length of the arc, this is almost like the radius, and this is the angle, and we all know the formula for that. So the length of the arc is nothing but radius multiplied by the angle, radius multiplied by the angle. This is like the arc, this is the radius, and this is the angle. Length of the arc is beta. Radius is almost like d, distance between the slits and the screen. It's almost the same because these angles are very small. So this is almost capital D, and that angle is delta theta. But beta is lambda d by d. Beta is lambda d by small d. So therefore, from this, you just get delta theta as dd cancels. You will just get it as lambda divided by d. That's how you get it. Okay, it's a very simple derivation, guys. I just done it for all of you so that you are very, very clear. So what is angular fringe width? Whenever you see these fringes, what angle do these fringes subtend from the center of the slits? that is called as angular fringe width. The actual distance between two minimas or two maximas consecutively, that is called as the just fringe width. Just the fringe width. So that is what has been mentioned over here. Fringe width beta is lambda wavelength into capital D by small d. Angular fringe width is lambda divided by small d. Lambda divided by small d, capital D is not there. Okay. Everybody fine till this point? Everybody learning these things in detail? Any confusion, any doubt till now? Please ask me and clear it off before we go ahead. Yeah. So remember, capital D is always that bigger one. Small d is always the smaller one. That way you will avoid the confusion. So that is one simple trick. Okay. Capital D is bigger of the two values. Small d is smaller of the two values. Number one. Number two, who is bigger? Between the slits and the screen, that is capital D. This is always small. So that is distance between the slits. That is small d. Distance between slits and the screen, when screen comes, it is capital D. Okay. Fine by me. Awesome. Okay. IT and aspirant, I will answer your question later on maybe. Okay. I just want to focus on the class right now. Great. Great. Now, after this, actually this concept should have come over here. Do I have a question on fringe width? This one. This was asked in this year only. So let's try and solve this question. In a Young's double slit experiment, okay, the setup is inside a medium whose refractive index is given. Separation is also given. Slits are also given. Fringe width is at so much distance. Sorry, the screen is at so much distance. What is the fringe width? All right. Now, usually if you had to solve this question, what you would do? You will say, sir, the fringe width is lambda d divided by small d. There is a small catch which was there in this particular question. Normally, if you had to solve it, wavelength, well, wavelength is given 690 nanometers. You can see 690 nanometers is given. So it will be 690, nano means 10 to the power minus 9. Distance between the slits and the screen is 0.72. So you're just going to put 0.72 over here. And small d, you can see this is a very small number, 1.5 millimeters slit separation. So you're just going to put 1.5 milli means 10 to the power minus 3. So that will be the answer of fringe width, but that is not the right answer for this question. Can you guess why? Can you guess why? Why there won't be central minima? The reason why there is no central minima is because at the center, both the rays will arrive together. So if a crest is generated here, a crest will be generated here. So when two crests will meet, they will create a constructive one. They cannot create destructive. Because for minima, it should be destructive, crest and trough. So if both are coming together, what will come? This slit and this slit, both will generate simultaneously. So 100% you will get a maxima, you cannot get a minima. Yeah. Got it. Yes, there is a concept of refractive index over here. So when light changes medium, do you remember when medium changes, medium change happens, when medium change happens, frequency is going to be constant. Speed of light is speed of light in vacuum divided by refractive index, not just speed of light, even the wavelength. So the new wavelength is the old wavelength divided by mu. That's the problem. So this will be no longer lambda, it will be lambda prime. And that is why this lambda prime will be this wavelength divided by the refractive index, which is 1.44. So whatever fringe width you will get, you have to divide it. That means it will become smaller. So hence, you can say the fringe width reduces. The fringe width, when you put it inside a medium, it reduces. That is very, very crucial for such questions. Now it is simple. You do the math, calculate, and you find the answer to be 0.23 millimeter. I have kept the same thing over here. It is 0.23 millimeter. So when you solve all of this, you are going to get this as 0.23 into 10 to the power minus 3 in meters. So forgetting minus 3 power, and you will write it in millimeters as 0.23 millimeters. Getting my point? So this kind of direct question has come in this year, and this year was considered to be a difficult set paper. Still, such questions have come. Yeah. Yes. Very good. Excellent. Now, imagine another question over here. Another question over here. Find the angular fringe width of a YDSC setup if capital D is 3.7 meters, small d is 0.3 millimeters, lambda is 600 nanometers. What is the angular fringe width? That is the question. Now, angular fringe width, I just told you the formula. It was wavelength by small d. Sir, there is no capital D. You are absolutely right. It was chumma given. It's a waste of, data. Okay, it is sometimes given for confusion. Lambda is 600 nano. So it is 600 into 10 to the power minus 9. 0.3 millimeters means 0.3 into 10 to the power minus 3. So 600, I can write it as 6 into 10 to the power 2, which will become minus 7. This I can write it as 3 into 10 to the power minus 4. 6 by 3 is 2. Minus 7 minus 4 will make it minus 3. But please keep in mind, this will be in radian. Okay, so the angular fringe width will come out to be in radians, not in degrees. So sometimes they give the answers in degrees. So you might have to convert it into degrees if required. So 2 into 10 to the power minus 3 into 180 divided by pi, that will be in degrees. Getting my point? If the options are there in degrees, you will keep the answer in degrees. Okay. Kritish, it is very simple to end the class. You just have to close the laptop or phone, turn off YouTube, Instagram is there, or Snapchat, I don't know what and all, Discord, or some game you can open very easily. It's very simple. If you want, I'll make a video on that also. Okay, very simple. You can end the lecture anytime you want. I don't have to do any effort. You have to make that effort to end the class. I don't. I have to make an effort to conduct this class. You have to make an effort to end the class. Open any app, any time pass app, and you can scroll some reels and maybe you can give some dopamine to your brain, and that will make you feel very pleasant and very happy, right? And probably you will enjoy that. Okay, great. Moving on. This is done. This is done. Fringe width is done. Okay. This is done. Okay. Now, the next thing is phase difference at any point from the part difference and the amplitude or the intensity and all of that, and how the intensity variation happens. So let's do that quickly. We already studied part difference at any point is d sine theta or yd by d. So if you want to find the phase difference at that particular point, that will be the path difference into 2 pi by lambda. So if you put delta x as this quantity, you are going to get 2 pi by lambda yd by capital D. That is the path difference to phase difference transformation. This formula you have already studied. Phase difference is 2 pi by lambda into path difference. So if you know path difference, you can find phase difference. Why will somebody need phase difference? The answer is obvious now. If you want to figure out what's the intensity of the rays meeting at that place for intensity calculations. Exactly. So if you want to know what is the intensity at that particular point, you will need this formula I1 plus I2 plus 2 root I1 I2 cos delta. That will immediately give you what is the intensity at that point on the screen. Simple. Is that right, everyone? Yes, perfect. Perfect. Simple. So, uh, with this, I think we should start doing some questions. Before that, these are all same things: intensity variation, I max by I min. You don't have to remember all of these things, but just these are formulas which we have done already before. This incoherent source, what will happen if instead of using two slits, you use actual two sources? If you use actual two sources, they are always going to be independent and they will be incoherent. That means they will not produce only any interference pattern, and you will see that the intensity will be washed out, the entire screen will be washed out, and you will see a constant intensity in the front of the screen, and it will be just I1 plus I2. It will just be simply I1 plus I2, nothing more, nothing less. All right. So that is one thing. And what happens inside a liquid also, I told you, if it is in air, the fringe width is this much. If it is in water, it will get divided by mu. Even the angular fringe width will get divided by mu. Any nth position will also get divided by mu. Everything shrinks, the pattern shrinks by mu times. Okay. So I think we should solve some questions on the this intensity aspect, which we have just discussed over here, so that you guys get an idea on it. All right. Let's see. Capital D, example, 2 meters. Small d, 4 millimeters. Lambda, 100 nanometers. Find the intensity on the screen at a point in front of one of the slits. One of the slit. That is the question. It's a very interesting question. Let's try to solve this. This is our screen. This is the central line. These are the two slits. This is S1. This is S2. This is D. This is obviously capital D. The point which we are considering is directly in front of one of the slits, meaning the rays of light will go like this from slit 1 and like this, and this is the point that I'm referring. So basically this particular point is at a distance of half the d, so that means this y coordinate will be small d divided by 2. Is that right? Everybody getting this particular point? Understood? This point is in front of one of the slits, and we want to figure out what will I get over there. Is it maxima? Is it a minima? What is it like the intensity going to be? In order to figure out the intensity, I will need delta or the phase difference, and for that we need path difference and all of that. So if you ask me over here, what is what is theta going to be? What is this particular angular position going to be? So this theta, I can find it out using the concept of trigonometry. So guys, tan theta will be almost theta, which will also be sine theta, which will be opposite side by adjacent side, y by capital D. Y is small d by 2, so small d by 2 by d, which means it will be d by 2 capital D. That is your tan theta, theta, sine theta, small angle approximation. Simple. Just using small angle approximation. So it is small d by 2 capital D. That is theta. From this, can we not figure out how much is the path difference? Remember, it was small d into sine theta in general. So therefore, it will be small d into sine theta is this number. So it will be d divided by 2 capital D. So it will become d square divided by 2 capital D. Great. All right. Sir, why sine theta? Uh, Sine and tan are same values. Remember small angle approximation when theta is small. So that's why tan theta and sine theta will be similar. And tan theta is going to be opposite side by adjacent side. Opposite side by adjacent side. Adjacent side is capital D. Opposite side is y, which is small d by 2. Okay, is that making sense? That is delta x. What about now? If I try to figure out delta phi, phase difference, it will be 2 pi divided by lambda into the path difference. That means small d square divided by 2d. That is the phase difference. Can I figure out how many radians is it? I think so. So 2 pi divided by wavelength is 100 nanometers. So 100 into 10 to the power minus 9 multiplied by d square, small d square, that means 4 into 10 to the power minus 3, but the whole square. 2 into capital D, D is 2 meters. Okay, so 2 pi multiplied by 4 square is 16, multiplied by 10 to the power minus 6, whole thing divided by 10 to the power minus 7. Yeah, and 2 2s are 4 over here. What is this number coming out to be? Well, 16 by 4 is 4. 4 2s are 8. So 8 pi is there. Minus 7 and minus 6 will cancel. And I'm left with 10 to the power minus 1, which will make it 80 pi, which is 40 multiplied by 2 pi, which is 40 multiplied by 2 pi, as you can see. What is this telling me? What is this telling me, guys? Quickly think and answer in the chat box. The moment I saw 80 pi, it is an even number. Tell me, what do you mean by this? Why y is equal to d by 2? Okay, I'll explain. Is it mentioned that the point is in front of the slit? The point is in front of the slit. This is one slit, this is one slit. So, this point is in front of the slit. Okay. This distance is d. So how much is this? D by 2. This is also d by 2. So the point exactly in front of the center, from there, how much will this distance be? It will be exactly this distance, which will be d by 2, d by 2, d by 2, d by 2, d by 2. Is that now making sense? Why the value of the y coordinate is small d by 2 now? Okay, clear? Yeah. Yes, it is an even number. So it has to be a bright fringe. It has to be a bright fringe. And for a bright or a constructive interference, we already know what that intensity will be. It will be root of I plus root of I. Remember maximum intensity whole square. So it will become 2 root I the whole square, which means it will be 4 times the intensity of any one of the slit. I is intensity of each slit, it will be 4 times of I. Very straightforward. By chance, it was not a good number 80 pi. Let's say it was uh, pi by 6. Chumma. Then what will you do? You'll use I1 plus I2 plus 2 root I1 I2 cos delta phi. That's it. That's the only difference. Getting my point? So if it was not coming out to be a good number, then it will be intermediate interference. And then I'll use I1 plus I2 plus 2 root I1 I2 cos delta. Great. This is how we can solve the questions. Amazing. Akka. Perfecto. Sure. Okay. Let's do one more question based on this. Let's do one more question. In a regular YDSC setup, find the least distance from the central maxima where intensity is half of the maximum, where intensity is half of the maximum. That's the question. Let's try and solve it. Lambda is given as lambda, d is given as d, small d is given as small d. In variables only we have to figure it out. So the intensity is half of the maximum. Okay. So in general, my intensity formula at any point would be I1 plus I2 plus 2 root I1 I2 cos delta phi. This is what it would be. Over here now, what happens is, first of all, both slits are same. Both slits will give same intensity. So I1 is equal to I2 is equal to I, number one. Common mistake which students do, they put IP as I by 2. That is wrong. That is not what the question is. The intensity is half of the maximum. So think, what's the maximum intensity that you can get? The maximum intensity, remember, root I plus root I whole square, which will be 2 root I, which will become 4I. This is the maximum intensity. So the intensity at that point, which is half of the maximum, which means it is 4I by 2, which means it is 2I. So the intensity at that point is half of the maximum. So maximum intensity is 4I. What is I then? I is intensity due to any one of the sources, S1 or S2. So when both the sources meet constructively, their resultant maximum possible intensity is 4 times of I. So that is the logic of this question, guys. So this is that screen. These are the two slits. So each slit is giving I intensity and I intensity. So at the center, you are going to get 4I. Some point you will get 2I. Some point you will get 0. So wherever you get 0, that will be your minima. That will be your minima. Wherever you are getting 4I, that is your maxima. So somewhere in between that maxima and minima, you are getting that point. Okay. Is that clear? So how do we solve this? Just start substituting it over here. Instead of IP, just put it as 2I. I1 and I2 are just basically I and 2 root I into I and then cos delta phi. I will get cancelled from everywhere. So it will be 1 plus 2. This is just 1 into cos delta phi. So 2 and 2 will cancel. So you will get 0 is equal to 2 plus cos, sorry, we'll get 0 is equal to 2 cos, delta phi. So cos delta phi has to be 0. So whose cos is 0? When the phase difference, is what? Pi by 2. Is that right? Cos 90 is 0. So we got phase difference is 90. Don't think actual angle is 90. It is the phase angle, which is 90. Now, how is phase angle related to the path difference, phase difference, everything? Come on, guys, try and recollect it. So phase difference is 2 pi by lambda multiplied by delta x, and delta x was dy by capital D. Remember that? So substitute it. So we will get, therefore, pi by 2 is equal to 2 pi divided by lambda into, instead of delta x, you will put dy by capital D. That's it. Instead of delta x, you will put this number. Pi will cancel. So we'll be left with 1 by 2 is equal to 2 d by lambda capital D multiplied by y. 2d by lambda d, y is there. So y will become, take these numbers on the top, lambda capital D divided by 2 2s are 4 times of small d. This is the answer. So exactly at this place, you are going to figure out that the intensity will be half of the maximum intensity. Is that clear, everyone? That's the y coordinate. Sir, why I1 is equal to I2? Because both the slits will be same in width, same size, so their intensities will be same only. So you take one slit, light coming out of it is I, other slit also, light coming out is I. Sometimes the intensities can be different also. I mean, that's possible. You can see some questions are there on that also. Like, for example, in a YDSE setup, one slit is 2 times the other times wider than the other. Find intensity at minima. Find the intensity at any minima on the screen. That kind of question also is there. See, what happens is, if this is your slit, okay, if you allow the light to pass through the slit, more the width, more light will pass. So the intensity out of a slit is directly proportional to the width of the slit, the width of the slit itself. So over here, one slit is 2 times wider than the other one, means if intensity 1 is I, then the second intensity is 2 times of I, because this is proportional to the width of the slit. So 2 times wide, 2 times more intensity. The question is now to figure out for minima. So for minima, the intensity is root I1 minus root I2. Remember, minus will be there, whole square. So root I1 is root I, root I2 is root 2I whole square. So what will this happen? 1 minus root 2. So 1 minus root 2 times of root of I, this thing whole square. So this will become 1, a minus b whole square is a square plus b square minus 2ab, great, into root I square into root I square. Okay, so root 2 square is 2, 2 plus 1 is 3. So 3 minus 2 root 2 times of basically I. That is the answer. So if one slit is wider than the other, then you will not see a perfect minima. There will be some intensity left, and it will not be a perfect dark region. It will be dim, but it will not be perfectly dark. This kind of question can also be there. Okay? Yeah. After YDSC, we'll have a small break. Don't worry. All right. Let's do some questions, guys, coming up on your screen. Few questions only are there. Okay. And then I think we are going to go to diffraction and other things. So let's do one of these questions coming up on your screen. In a YDSC setup, interference pattern, second minimum is observed exactly in front of one of the slits. Second minima. The distance between the two sources is D. Distance between source and screen is capital D. The wavelength of the light used is. A very similar question. Instead of intensity, it's something else. Diagram wise, it is very much similar. This is your screen. This is your central line. These are your two slits. So this is S1, this is S2, this is the central point. You are considering a location which is in front of one of the slit. So this is the point which is under consideration. So think now, if this entire thing is small d, it is obvious now this thing over here is small d by 2, which is also basically the y coordinate of this point. So the y coordinate is small d by 2. The y coordinate is small d by 2. The wavelength is asked, and the distance between the two coherent sources is also given. What are you going to do, guys? Come on, think and tell me. What will you do? It is mentioned which minima is this? This is given to be second minima. Second minima. Second minima means what part difference? 1 lambda by 2, 3 lambda by 2. Oh, 3 lambda by 2. Guys, it is the third, it is the second odd number, which will be the number 3. So keep that in mind. So my y coordinate is odd number times by 2, lambda capital D by small d. My odd number will be 3. How many of you got it? It can't be 2, no? Odd number can't be 2. It has to be odd. So first minima will be 1. Second minima will be 3. Third minima will be 5. Fourth minima will be 7. Fifth minima will be 9. So that is how the numbering goes. And this y value, that is nothing but small d divided by 2. Just have to rearrange, guys. So lambda will be 2 goes with this d and this d. This, oh, sorry. First of all, these two 2's will cancel. So d will be 3 capital D by small d into lambda. So lambda will be d square by 3d. D square by 3d, which is option B, of course. There you go. That is the answer. Simple, easy peasy, lemon squeezy now. Are you getting a hang of this chapter now? How many of you are slowly getting some confidence after attending this lecture? Smash that like button, put some heart likes in the chat box and even in the comments. Sir, now I am understanding because I am doing it conceptually. If you are till this point doing it formula wise, every time you would be like, sir, every time I'm getting stuck, I'm not able to apply it in the question. Yeah? Okay. Let's do more questions on your screen, and here it comes. Year 2025. In YDSC, one of the slits is covered by red, another by green. What do you think will happen? One is red, one is green. What will happen? One slit will give out red light, one slit will give green light. Red light will have a completely longer wavelength. The green light will have a slightly shorter wavelength. So because of that, you will not see a perfect interference. To see that interference, the sources should be coherent. There should be of the same wavelength, same phase difference should be there. But nothing like that will happen. So you will not at all see any kind of interference fringes. Yes. You will not see only any interference fringes. Very good. Very good. Now, there is one interesting question which is also asked. I will help you with the formula. What they tell is a glass piece is kept. A glass piece whose refractive index is mu, thickness is t, is kept in front of one of the slits. In front of one of the slits. Find the shift in pattern. Let's understand why it will shift, and then we'll figure out what is the shift. What do I mean by this question also? Let's figure it out. So this is our screen. This is the central line. That is capital D. Our two slits are over here, S1 and S2. Okay, perfect. Now, what happens usually is that when there is no glass slab, nothing as such, then both the rays will meet together over here, and you will see delta x will be 0, which will be our central maxima. Central maximum. This is your normal YDSC setup, normal Young's double slit experiment. Nothing great about it. But the moment you take a small glass piece and place it in front of one of the slits, think what will happen now. Okay, think what will happen now. You take the same rays, S1 and S2. This will reach here, but this won't reach here so fast because it is slowed down. So the funny part is at this particular point, delta x is no longer 0. So there is no central maxima. There is no central maxima. Oh my God. Why is this happening? Because this is fast and this is slow. Are you getting my point? Why it has been slowed? Because of this glass piece. Oh my God. So, sir, where will the central maxima or where will the 0th maxima be? It's not right to say central maxima. There is no 0th maxima here. No 0th maxima over here. So where will that 0th maxima be? Because this ray is already reached, this ray is still here. It still has to complete some distance because it has been slowed down. The answer is, think logically, if this is slow, you will give it an advantage. I will tell that ray, okay, you are slow, right? You travel less distance. Oh, you are fast? Do one thing, you go more distance. So then both of you will catch up and meet at the same time. So what I will do then is I'll ensure that this ray will only travel this much and this will travel slightly more. So in that process, because this distance is shorter for the slower one and this distance is longer for the faster one, they will compensate somewhere, I don't know where, and probably somewhere over here, my delta x will be 0. Delta x will be 0. This means my 0th maxima has shifted by this much amount. So this is basically the shift which has occurred, and I will call that as y. Did you understand it? So the entire pattern gets shifted as it is, but there is no change in fringe width. No change in fringe width, which is basically beta, but the entire pattern shifts. The entire pattern shifts in one place. How many of you understood this concept till this point? Yeah, very good. Excellent. Sir, now how much will that shift be? I'll tell you one simple technique, very mind blowing. See, bro, if the glass slab was not there, these two rays will have some part difference because of actual distance, lengths. But that has been compensated by this glass slab. So, can I say because delta x net is 0, delta x net is 0, so the path difference due to the slab is compensated magnitude wise, compensated by actual delta x in the length of the path, in the length of the path. One is more fast, one is more slow, other one is longer, one is shorter. So they both are compensating. Due to path difference, recollect the due to the actual paths which are different, the path difference is, remember, d sine theta, or you can put dy by capital D. Due to a glass slab, I did it before over here when I told you due to a glass slab, what is the part difference? Thickness of the slab into refractive index minus 1. So go over there and just say this is nothing but the thickness of the slab into mu minus 1. That's it, equal to. Now you are just going to get the shift value. So therefore, y is equal to t into mu minus 1. Everything is fine. Yeah. Capital D divided by small d. Capital D divided by small d. This is the answer. So this is the amount by which the entire fringe pattern will get shifted. Is it simple now? Is it simple? Remember this formula, okay? Remember this formula, my dear warriors. Very useful formula for all of you. T into mu minus 1, capital D by small d. That is the amount by which the pattern gets shifted. Direct questions have come on this. Direct questions have come on this. Like a slab, okay, just like this thing is given in variables, they have given it in values. A slab of maybe I don't know, 0.5 millimeters and refractive index 1.5 is placed in front of a slit. Is placed in front of a slit. Small d is 2 millimeters. Small d is 2 millimeters. Lambda is 400 nanometers. Capital D is, let's say, 1 meter. Find the shift. Find the shift. Or sometimes, you know what they do? They ask something like this. Okay, small d is, let's say, 2 millimeters. Find, okay, find, they might ask you capital D, find lambda such that it shifts by 4 fringes, such that it shifts by 4 fringes. That kind of question also can come. So all these basic values are given and they tell you the pattern shifts by 4 fringes. So just imagine this pattern was there, this particular pattern was there, and this entire pattern has got shifted by 4 times of beta. The entire thing got shifted by 4 times of beta. So start using our formula. Our shift is given by thickness into mu minus 1 into capital D by small d. That's our regular formula. Capital D by small d, t into mu minus 1. That's the shift. Now, how much is the shift given? The shift is given to be 4 times of beta. Thickness is given to be how much? 0.5 millimeters. Mu is 1.5. This is 0.5 millimeters. Thickness is 0.5 millimeters. Refractive index is 1.5. Distance between the slits is given to be how much? 2 millimeters. Capital D is not given to me right now, so I will not put it anything because both are in millimeters. I have just kept it as it is. I have not changed the units. Beta, do not forget, is lambda capital D divided by small d. Lambda capital D divided by small d. And if you want, I need not even put this over here. Just put this as it is. So 0.5 into 1.5 minus 1 multiplied by capital D, whole thing by small d. Best part is D and D. This D and D will get cancelled. So I will get lambda is equal to 0.5. 1.5 minus 1 is again 0.5. This is the number 4. So that 4 will come here. But do not forget this was in millimeters. So keep it in millimeters. So 0.5 into 0.5 is 0.25, which is again 1 by 4. So it will become 0.25. And this 1 by 4 is also 0.25. So again millimeters. So 25 into 25, 625. So it will become 0.0625 millimeters. 0.0625 millimeters. If you want 1, 2, 3 decimal places, you can shift it, and 62.5 micrometers. That will be the answer. Is that okay? How to solve this particular question? Everyone? So this kind of questions can also come where numerical values are there. They give you the shift and they ask you to find the wavelength, or wavelength is given, they ask you to find the shift. All sorts of questions are possible. Okay. Please keep in mind the units. I have maintained the units every single time. I have maintained it in millimeters. Just that this D and this D just got cancelled. Capital D also got cancelled. So it became very simple, even if capital D was not there. So these are some of the questions on YDSC setup. I think these were some brilliant questions which you have learned today. Okay. So intensity, fringe shift, a pattern is moving here and there, all of that. So it's time for diffraction and this thing. What do you say? Mm, Polarization, but we'll do it after a small break. Okay. I also need some break, guys, because or else my throat will go. Okay. So we'll just take a break. Meanwhile, you guys like the session in case you haven't liked it yet. Yeah, very, very important. So let's take a 15-minute break maybe. Welcome back, guys. It's time to continue with the last two small topics, which is diffraction and polarization. Ready for it, guys? Yeah, ready? Shall we begin? Everyone, fire up the chat box quickly. Call up all your friends. Even if you're watching diffraction independently, it's fine. Even if you're joined in late, it's fine because this is a new subtopic or article in the chapter of light waves. Come on, guys. Fire up the chat box quickly. I'm audible, visible. Hi, Ibu. Looks like the Sigma crash batch is done. Okay. Yep. Welcome. Don't take break now. Yeah, no break now. Now it is one shot. What's the time? It's yeah. By 11:30 we should be done. Yeah. And remember, tomorrow morning also 6 o'clock I have class. So guys, when Shreyas Sir is doing so much of hard work for you guys, it is your duty, your responsibility that you show up without fail in live class. Recorded to anybody can watch. Live class is your responsibility now. Okay? Cool. Let's go. Let's go. This video is useful for boards in conceptual and problems point of view, but for writing answers for boards, not so much because concepts and problems, assertion, reason, objective, or even numericals, that part you can do. But those writing, give reasons, case study, and all that, obviously you'll have to do a board specific lecture. Okay. All right. Yeah. Muguntham, you are quite late for the entire class, but for diffraction, you're just on the right time. So, what is diffraction? Diffraction is basically the phenomena where light entering through a hole, through a gap, through a corner, it bends and it spreads. That is diffraction. Like the wavefronts of light were going, it encountered a gap, slit, hole, aperture, and it begins to spread all around. That bending of the waves is called diffraction. And the bending depends also on the wavelength and how much the width of the slit is. So accordingly, you will see more or less bending can happen. And to see that, let's have a look at animation right over here. Right now there were two slits, so let's make it one slit and see what exactly happens when I turn on the light. Okay, I have to press play. So let's have a look. Oh, there you see the light spread. Can you see? And it is going to spread on that particular screen. We can just move it here to see what exactly is happening. There you go. That's a single slit. So for that, we have different slit widths also we can take. And you can see if I change the slit width, the spreading also differs. The spreading also differs. Oh, now this has become bright. Okay, if I make this smaller, you can see this pattern will change. Obviously, yeah, this will change a little bit. Okay, there you go. This has again changed the moment I change the slit width. So that is how the slit width and the wavelength also, if I change, things will be different. You can see that. Okay, I will use some bright color, blue color over here, and see how the pattern is formed over here. The bending depends on everything. Now you can also see diffraction for an aperture. Like, for example, this is a laser light, torch light. There is a cardboard piece with a hole in it. This is a small image of it. This is the big image of it. I can change the hole size. You can see the hole size will become small or big over here. Okay. And this is the zoomed in image. This is the screen on which I will see what is exactly observed. So if I turn on this light, it passes through the hole and it spreads. If I change the hole size, you can notice how the pattern which is formed on the screen also changes. If I make the hole too big, it is a different thing. If I make the hole too small, it is a different thing. So this is again diffraction. Even I can make it square shape, circle, or many circles. So you get these diffraction patterns out there. Okay, this is the diffraction which you get. So this is the bending of light when light passes through a hole, aperture, opening, slit, or a corner. That is diffraction. Great. Now, why does this exactly occur? There is a beautiful explanation for that, and that will actually blow up your mind. And sometimes we define diffraction and interference in so nice way, but then you realize actually it's not so easy if you think about it. And I'll tell you why. Look at this. When light is entering into a slit, what happens is, by Huygens principle, each point between the slit acts like a source, and there are infinite points, so there are infinite sources. Now, all these infinite sources produce many wavefronts, and think of this as many Young's double slit experiments. Like in Young's double slit experiments, what do you have? Two sources, right? So imagine one source here, one source here, one source here, one source here, one here, one here, one here, one here. So like that, so many pairs of sources can be formed between these two, these two, these two, these two, these two, these two, like that. So if you start making those pairs, you will have many Young's double slit experiments. Now, each of these Young's double slit experiments will produce an interference pattern on the screen, and that is why you see interference of these infinite point sources on that gap. So, actually speaking, when I say there is a diffraction happening, when I say diffraction happening and I'm seeing patterns, bright, dark regions I'm seeing, it is actually that every point in here is acting like a slit or a source, and each of these points are creating interference with the next one, with the next one, with the next one, and you're getting a net interference here. So, if you ask me what is the difference between interference and diffraction, I would actually be confused, because even diffraction is interference, but that interference is happening within those points of a slit. Whereas that Young's double slit experiment, you have two such slits, and each of those slits is producing interference. But the crazy part is, when we studied Young's double slit experiment, we never bothered about, sir, in this slit also, because there are multiple sources, this slit will itself produce its own diffraction. The second slit will produce its own diffraction. And then both of them together will produce your regular YDSC interference. So actually in Young's double slit experiment, you're getting three kinds of patterns, out of which we are ignoring the two. The two that we are ignoring are the diffraction. Otherwise, it becomes a crazy analysis, which is not there in JEE syllabus. So, to repeat again, coming back, when we take a single slit, each of the points within the slit acts like a source, and each of these sources at any point will have many rays coming and meeting at that point and create an interference. The moment I will take two slits, slit will produce diffraction, this slit will produce diffraction, and these two slits together will produce interference. So three patterns together which are forming on the screen. But we ignore the diffraction pattern because usually it is faint, and the second one also. So the only thing we consider is the interference of the light rays from the two sources, from the two slits. Is this concept clear in your head? Let me know. Because when you have a single slit, it is its own individual pattern which will anyways be there even in a YDSC setup. But it's just that we are ignoring this because the light is spreading very nicely over here. How many of you got it? If there are infinite points as a source, then how do they have a net interference? Why do they don't cancel? Or maybe, no, you're not dumb, Nitesh. It's a very valid question. So basically what happens is, in infinite sources, each source will produce, if you take in vector form, some amplitude, then next amplitude, then next amplitude, then next amplitude, then next amplitude, and so on and so forth. And this was the last source. So if you add all of them together, you will get a resultant vector, that will be basically your maxima. That will be basically maxima or bright region. And when each of these sources, they produce vectors like this, so that it becomes a closed polygon, then the net resultant is 0. So then it is basically a minima. Then it is basically a minima. So some places it is maxima, some places it is minima, depending on how each source is producing their wavelengths with what phase difference with the next one. The next one will be at a slightly different phase angle, different phase angle, different phase angle, different phase angle. So if you take those small vectors of those amplitudes of each of these sources and add them vectorially, the resultant is the net interference that you get. Sometimes it is maximum, sometimes it is a minimum. That's how it is. Is that okay, Nitish? Perfecto. Sir, is it different for all colors? Yes, it will be different for all the colors. Yeah. Yes, the intensity, will it change with the wavelength? Not necessarily, but there is a formula for that. We don't go too much into that intensity formulas because that's not again there for JEE, but I'll give you the formula today also. Anyways, but if you understood what is the difference between interference and diffraction, that is a very important thing. Now, there are two kinds of diffractions that we study, but you should just know the theory of it. Maybe it can come in boards, maybe it can come as a statement based question in JEE itself. First is Fraunhofer diffraction, second one is Fresnel diffraction. Fraunhofer diffraction is where the source and the screen are very far away. So by the time the wavefronts will come, they are almost parallel. But in Fresnel diffraction, the source and the screen at a finite distance, and you will see that when the light rays come near the slit, the wavefronts are curved in nature and then they will bend. So basically here you have planar wavefronts, here you have curved wavefronts, cylindrical kinds or spherical kinds, which are going to fall on the slit. That's the main difference. So Fraunhofer, big name, yeah, Fraunhofer, big name. So large distance, infinite distance. So planes wavefronts. Fresnel, short name, short and sweet. So distance is small. That's how I remember it. And the wavefronts are also curved in nature. In Fraunhofer, you will get a very intense interference pattern. Here, it is not so intense, but yeah, it is observed still. These are the main two differences that you should be aware of. Okay. Now, coming to the formulas, guys. Coming to the formulas. Position of maximas and minimas of the diffraction pattern. Now, the formula that we learn is mainly for Fraunhofer diffraction. Basically, when the slits are very far from the source, so the rays are almost parallel onto the slit. Now, each point between that slit will act like a source. They will all produce some interference on the screen. They will all produce some interference on the screen. You can see so many rays are going and meeting that point. So if theta is the angular position of the point on the screen, P0 is the central point, P will be anywhere. It will make some angle with the central line. Then the path difference is given by B by 2 sine theta. B is the slit width, or A by 2 sine theta. A is the slit width. So A by 2 sine theta is the path difference. Remember, it is very different in YDSC. In YDSC, it was D sine theta. Now it is D by 2 sine theta. Basically, that B or D or A is not the distance from one slit to the other. No. It is the slit's width, not distance between the slits. Understand the difference. It is the actual width of the slit. Okay. Okay. Sir, small question. If you increase the number of slits, would there still be some interference like 10? So it seems like it will show interference, but if you go many slits, yeah, so that's what. There is no clear difference between interference and diffraction. So when do you call it as a diffraction? Actually, when there are infinite sources which are considered, technically then we call it diffraction. But interference is when you have countable number of sources and then you are seeing the interference. That's when you call it interference. But still, when there are infinite sources, what they are doing is still called interference. So technically, it is very difficult to segregate difference between interference and diffraction, and that is also a line which is mentioned in NCERT also and in many books. So we very conveniently say diffraction is when there is one slit and interference when there are two, three more or five slits. But even within the slits, there are infinite sources. So even they are interfering. So what do you mean by interference then? Aren't those infinite sources within the slit also interfering? They are. So then isn't diffraction at the end of the day interference? Exactly. So best way to understand it, diffraction at the end of the day is just interference of infinite sources. Is that clear, Nitish? Okay. Now, what is basically the condition for the dark fringes? The condition for the dark fringes obviously is the path difference should be n times lambda by 2. So in general, 2 will cancel. You might have n. So in general, it will be b sine theta is n lambda. B sine theta or A sine theta is n lambda. That is the condition for the dark fringe. Remember, sine theta means opposite side by adjacent side and all of that. You can still use approximations. Sine theta is tan theta. Now, if you ask me, what about the dark fringe? This is the dark fringe, guys. Second. This is the dark fringe. So for the dark fringe, this is the one. For bright fringe, this is the one. I by mistakenly said dark fringe again. My bad. So for dark fringes, you are just going to use A sine theta is n lambda. Let's use the same symbol. Let's not change it again and again. Let's say it is B. B sine theta is n lambda. N can go with 1, 2, 3, 4, 5, and like that. Those are the minimas. But for bright fringes, the formula is very, very important. B sine theta is 2n plus 1, very, very important, by 2 into lambda. Here I would suggest remember this result rather than putting it as odd number lambda by 2. Although it is technically an odd number by 2 into lambda, odd number by 2 into lambda technically. But still remember this as 2n plus 1 by 2 into lambda. Why? I will tell you. Okay, this is very important. See, if you take our screen here, you are going to see a bright fringe over here. This is central. Then you are going to see a dark fringe. This is your first minima. In the case of first minima, in this formula, n will be 1. So n will be 1. So over here, you will use n is equal to 1 in b sine theta is equal to n lambda. So the value of n that you will put will be 1. Then again, after some time, you are going to get your maxima over here, then maxima over here, and so on and so forth. Over here, you are going to get your second minima. And when you get second minima, in the value of b sine theta is equal to n lambda, you are going to put the value of n as 2 for second minima. But observe this carefully. For this is central, or basically I can call it 0th. For the first maxima, this is second maxima. Keep this in mind now. Very, very crucial. Very, very crucial over here. For first maxima, keep in mind the value of n will be 1. So 2 ones are 2 plus 1 is 3. The odd number that you are going to get will be will be basically 3 times, because logically speaking b sine theta is 1 lambda here, so the next number should be more than 1 lambda. So lambda by 2 is not more than lambda. 3 lambda by 2 is more than lambda. So over here, your b sine theta will be that odd number by 2 into lambda, right? That odd number that you will be putting is the number 3. The biggest catch in diffraction. Many people do not know this. So second maxima when you put and you say b sine theta is odd number by 2 into lambda, that odd number over here is actually 5. That is why I'm saying better to stick with 2n plus 1 by 2 into lambda, where n is the bright fringe number. First fringe bright, second fringe bright. So if you put it, it becomes very easy. How many of you got it now? How many of you got it now? This is very, very crucial, guys. Keep this in mind. It is not lambda by 2 because lambda by 2 will be somewhere here. This is 1 lambda. This is 3 lambda by 2. This is 2 lambda. This is 5 lambda by 2. So 1, 1.5, 2, 2.5, 3, like that it will continue. Got it? Everyone with me on this? Absolutely clear? Excellent. So now that you have understood this till here, let me also tell you that how will the intensity change in the case of Fraunhofer diffraction. This is the interesting part where actually the intensity of every maxima is different, whereas in your YDSC experiment, every maxima has the same intensity. Here it is not the case. The 0th maxima is very bright, next one is very less, even less, and it just dies out. So the most prominent one are the first 2-3 maximas on either side. So the intensity of the maxima itself reduces, and there is a formula for that. I naught sine square beta by beta square. Okay, I naught sine square beta by beta square, where beta is the fringe width basically. Okay, so coming back again over here, I'll repeat because some students still had that doubt. See guys, central maxima, let's focus on this in that b sine theta. Over here, my b sine theta will be n lambda. That n will be basically 1. This over here, this is 0 lambda. This is 0 lambda. After 0 lambda, what should come? 1 lambda will come. But keep in mind, lambda by 2 is not a minima or a maxima in diffraction. That is the catch. So, this is the formula for your minima. B sine theta is n lambda. N will be 1 lambda, 2 lambda, 3 lambda, like that it will go. So, when you get 1 lambda, it is first minima. When you get 2 lambda, it is second minima. 3 lambda, third minima. So, after maxima, you should get minima. After minima, you should get maxima. So, the maxima, whatever number you will get over here, b sine theta, that should be more than 1 lambda. So, who is more than 1 lambda? 3 lambda by 2. And it is also in between the next 2 lambda. Between 2 lambda and 1 lambda, who is in between 1.5 lambda, which is 3 by 2. So, that is why the first maxima starts with 3 lambda by 2 on the right hand side. Second maxima, 5 lambda by 2. There is no there is no just lambda by 2 in a diffraction pattern. That is what my point is. The numbering only starts with 3 lambda by 2. Okay? Is that now clear, Vishwanath, Rajkumar? Okay? So if you do it 2-3 times, you will get it. Minima, 1 lambda, 2 lambda, 3 lambda. Maxima, 0 lambda. Then directly 1.5 lambda. And then 2.5 lambda. That's how it goes. So on the right hand side, this is 1 lambda, this is 2 lambda, then 3 lambda. Over here, this is 0 lambda, this is 1.5 lambda, this is 2.5 lambda. Now I think it is clear. The 0.5 lambda is missing. That's the whole point. Okay, clear? The other thing which I told, in Young's double slit experiment, the intensities are constant for all maximas, but in case of diffraction, it is not the case. The first maxima, next maxima, third maxima, they keep on reducing with intensity. The only prominent ones are the first few maximas. After that, the intensity is so small that it becomes negligible. Okay, keep that in mind. So, if you ask me the difference between interference and diffraction, here it is. In interference, you are superimposing two or more waves, okay, together of the same frequency or wavelength. In diffraction, you are imposing waves which are, diffraction, you are imposing two or more waves coming from two parts of the same wavefront. It's not two different sources, same wavefront, you are taking two sources on it and you are interfering those waves. In interference, all the fringes are equally bright. In diffraction, the central is bright, next one is dim, third one is even dimmer. In in interference, all dark fringes are perfectly dark, perfect destructive interference. But here, all dark fringes are perfectly dark, but their contrast with bright fringes and width decreases with angle. So what happens is, in case of your interference pattern, you get nice fringe widths, beta, 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 like that. But here it is not the case, because what happens is the brightness of the bright fringe reduces, so the contrasting nature which is there, that goes off. This is too bright, this is less bright. So the dark part which is there, here it might be very narrow, here it will be wider, here it will be even wide, because you will see the next bright fringe is very less bright. So that contrasting nature gives you that feeling as if those dark fringes are becoming wider and wider. It makes you feel like that. Understood? Because next one, instead of being so much bright, next one is this much bright only. Next one is even lesser bright. So in between portion which is blank, that blank part increases, giving you that notion. Interference, bright and dark fringes are in large numbers. In diffraction, bright and dark fringes are in small quantities, not too many. Because after a point, the intensity goes off so quickly that you are hardly going to see it. But in normal Young's double slit experiment, you will see 10, 20, 100,000 fringes also. That will not be the case in diffraction. So this is a very important table. Okay, keep these things in mind. Now, the only thing left over here is the width of the central maxima. Okay, let's talk about it. This is our screen. This is the central bright fringe. Next bright and next bright is over here. This is central bright fringe. Your first minima will be here. First minima will be over here. And first minima will be over here. Now, if you take the distance from the minima to the next minima, because this is where you get perfect dark, so the brightness will gradually reduce. Try to visualize this. Brightness will gradually reduce over here. This though will be too bright, okay, and here it will be less bright. It will completely cut off over here before again doing the same thing over here. Try to visualize this. It's too bright, dim, 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 dark. This is where it is cut off. So the central fringe is getting cut out here. So this is the width of the central maxima. This is W, which is also called as the width of central maxima. central maxima, symbol is W. How much will it be? It's logical now. This is the absolute center. So this W will be two times the distance from the minima to the central bright fringe, two times Y I will call it. This Y is basically your distance from first minima. Basically, this is your Y. So whatever is this Y is the answer for it. But how much is that Y? Well, I know if you want to look at minimas, we have to use this formula, B sine theta is equal to n lambda. So using that, so B sine theta first minima, so n value will be basically 1 into lambda. But sine theta is nothing but tan theta. So that will be lambda. So this is approximate. And what is the value of tan theta? Tan theta is y divided by base. Remember, this is that base, correct? And if you think about it, it goes like this, okay? And of course, this is theta. So tan of theta is y divided by the base, that is equal to lambda. So from this we can get y. Y is lambda d by small b. Hence my width will be, how much? 2 times lambda capital D divided by b. That is the answer. This is the width of the central maxima. Everyone got it till this point? Everybody got it till this point? This is the width of the central maxima. Some books also give you what is the angular width. What is the angular width? So this will be also theta. So the angular width of central maxima, that is delta theta, will be 2 times of theta, which is 2 times of approximately, you can say tan theta or sine theta, whatever you want to use. So 2 times of, let's say, I put tan theta, and tan theta from here is lambda by b. So it is nothing but 2 times of lambda divided by b. That is your angular fringe width. That is your angular fringe width. Is that okay, everyone? Angular fringe width. Perfect. Okay. So these are your typical formulas which you need to remember. So till now, what we have done, what is diffraction, how it occurs due to multiple points on that wavefront interfering with each other. The path difference in general is b by 2 sine theta, b by 2 sine theta, and from that you get, for dark it is b sine theta is n lambda, for bright it is odd number by 2 lambda. But remember that odd number starts with the number 3, not 1. That's the catch. The odd number starts with the number 3 for maximus, not with the number 1. And the width of the central maxima is 2 lambda d by b, and angular width is 2 lambda by b. This is very similar to that, remember, fringe width, angular fringe width and all of that, except for the number is 2 is not there. Why 2? Because from here to here, so this y and this y will become 2y. That is the reason why that 2 times is there. Is it now clear why that number 2 is there? This to this is the entire width. So if this is y plus y. I hope it is clear now. I hope Lewis, Suresh, that doubt is clear now. Okay, because that number 2 only causes that problem. Y3? Y3 I explained, no, some time back. This whole thing I explained. I took 5-10 minutes. Just rewind the class little bit behind. I have explained this. TV gaming. Okay? Because the minima formula is, See, I'll tell you the main thing with diffraction, no, there is no actual formula for maxima. So this is an approximate formula. The only formula you know is for minima. So if I know the minima is going to start with 0, sorry, 1 lambda, then 2 lambda, then 3 lambda, then after minima only you will get the maxima. So if this is 0 and this is 1, the maxima has to come between 1 and 2 at 1.5. 1.5 means 3 by 2. So that odd number which comes is 3. Between minima and maxima, you can't get another maxima. So the maxima has to come here. So understand like that. Okay. TV gaming, Tanuja, Suresh, Lewis. So concepts are there. It is not formulas. Concepts are there. In a single slit diffraction pattern, identify the incorrect from the following. The fringes have unequal width. The fringes have unequal intensity. Fringes have unequal width and unequal intensity. Fringes have unequal width and equal intensity. Straightforward now. If they twist the question, we derive the formula however we want. Yeah, use the part difference formula. That's all. The fringes have unequal intensity, 100%. The fringes have unequal width, 100%. The fringes have unequal width and unequal intensity. Yes, the fringes have equal width and equal intensity. Wrong. The question is which of the following is incorrect. So the incorrect option will be D. Yeah. I just now told you the intensity keeps on dropping, and also because of that fact you feel the fringes are of different widths. So fringes are also of the different widths and the intensity is also lesser and lesser. So it is option D. So fringes have unequal width. That is correct. Right over here only I showed it to you. See this? I showed it to you here. Okay. That the fringes are of unequal widths. It's wider than smaller. It's only because intensity drops very quickly and you feel that the width is reducing over here because of that. Okay, clear? So you should know this fact. It's not like your Young's double slit experiment. Next question. Consider the diffraction pattern obtained from the sunlight incident on a pinhole of diameter 0.1 micrometer. The diameter of the pinhole is slightly increased. It will affect the diffraction pattern such that the size increases but intensity decreases, size increases, intensity increases. All four combinations are there. Okay, think about it. What are you going to do? If you recollect the formula, B sine theta is n times of lambda. So if you take sine theta, which will be n lambda by B for a minima, now it is mentioned that if you are changing the diameter, you are increasing it. That means the slit width you have increased. So sine theta or theta will decrease. So earlier, if this was the central line, this was the screen. Earlier, if you are getting initially over here the minima, because theta will reduce, you will get the minima over here finally. So originally this was your theta. Now this is your theta. Minima is becoming closer to the center. So the size of the pattern is reducing for sure. So size is increasing wrong. So the size is definitely decreasing. The size is definitely decreasing. Now if the width reduces of that pattern, the width reduces of that pattern, what happens is that intensity, that energy has to go somewhere. So if earlier the intensity graph looked, for example, if the intensity graph looked something like this, it was wider. The moment it becomes narrower, that energy has to go somewhere. So when it becomes narrower, you will see the graph will become like this. Sorry. So the fringes will become more brighter because that energy has to go somewhere. So it will essentially become brighter. That's all. It's very simple to understand via energy terms. Whatever energy is coming from before, it has to be conserved. So earlier that energy was distributed on a larger area. Now it is distributed on a smaller area. So the intensity will increase because more energy is falling on a small area. That is the logic between that. Okay, so I think it should be C option. Let's figure it out. Yes, it is option C. So these kind of questions have come examination. Next question on your screen, here it is. A single slit diffraction pattern is formed with white light. For what wavelength of light is the length lambda? Okay, maxima is asked. So when maxima is asked, remember the formula is that odd number thing, 2n plus 1 lambda d by b and all of that. Okay, so you will have to think about it. So the formula that I'm going to use is 2n plus 1 by 2 into lambda is equal to b sine theta. Now, as per the given information, they are coinciding. If they coincide, that means sine theta or theta is going to be the same. B is not changed. This is the same because it's the same slit. It's just that I'm changing the lambda. So the product of these two will change. That's all. So hence I will say 2 into n plus 1 by 2 into lambda will be 2 into n plus 1 by 2 into that other lambda. So let's say I want to find that lambda prime. So it should coincide with the third maxima of the pattern of the light of wavelength lambda. So when wavelength is lambda, it is the third maxima. Third maxima means I should put the number 3. Okay, this third maxima of wavelength lambda. So wavelength is lambda and this is third maximum. It should be the fourth maxima. So I'll put the number 4, but I do not know what wavelength it is. So that's why I'll put lambda prime. 2 cancels. 2 3s are 6. 6 plus 1 is 7. So 7 lambda. 8 plus 1 is 9. So 9 lambda prime. So lambda prime will be 7 by 9 times of lambda. That is the answer. So 7 by 9, which is option B, of course. That is the correct answer. It's that straightforward, guys, most of the times. Okay? Clear? Everyone? Pakka? Okay. Now, I will tell you one last thing before going ahead, and then we'll go to polarization now. Okay, we'll go to polarization. Let's say, example, our wavelength, chumma I'm taking, is, fixed, and let's say it is 2 millimeters. Chumma I'm taking some random value, 2 millimeters. And I'm allowed to choose the slit width. So, the slit width B can be chosen. Can be chosen. Okay. Now see what and all will happen. Imagine in the first scenario, I choose, because remember our formula between minima and maxima is B sine theta is equal to n times of lambda. So let's say in the first situation, I am choosing the value of B as example 4 millimeters. So what will happen is sine theta will be n times lambda. Lambda is 2 millimeters divided by B, which is 4 millimeters. So it will be nothing but n divided by 2. So sine theta is n divided by 2. That means since sine theta always has to be less than 1, it can't be even equal to 1. Remember, theta can't be 90 degrees exactly. So in that situation, my value of n by 2 also has to be less than 1. Basically, n will be less than 2. That means n can be only till 1. So is that what it means is that I am going to somewhere figure out that there is a minima on the screen. So on the screen, somewhere I'm going to see a minimum, and probably the diagram will look like this. So maybe this is that place. This is that place where you are going to see n is equal to 1. N is equal to 1. And again, after that, you'll probably see a very faint, bright region over here. This will be the region of, pure darkness, you can say. This will be a region of pure darkness. So somewhere on the screen, you are going to see a pure dark region and using this formula. That is in this scenario. Okay. Number one. Now just imagine if I choose my value of B exactly as 2 millimeters. If I choose my value of B as 2 millimeters, then sine theta will be n, lambda is 2 millimeters divided by 2 millimeters. That means it will be equal to n. Sine theta will be equal to n. But since sine theta always has to be less than 1, so n has to be less than 1. That means it is non-existent. Non-existent. It is basically non-existent. What it means is that on the screen, what you are going to see is that the pattern will be so much spread that the final minima is going to come towards the end, literally. The final minima is almost going to come towards the end. Yes, the minima very, very far away minima. It means also the entire screen is illuminated as the central maximum. Illuminated as central maxima. So when my width of the slit is larger than the wavelength, then I will see pattern bright, dark, bright, dark, bright, dark. But when my slit width is equal to the wavelength, I am seeing the entire screen is illuminated. That is why you would have seen in many places that diffraction is best when the width of the slit or the opening is near to the wavelength, because it will spread everywhere. There is not even one place where you are going to see its absence. Is this concept clear in your head? Let me know in the chat box. How many of you got it? I bet on this you would not know, and many teachers do not touch upon this concept by playing around with B. So when B is more, so the conclusion is when your B is more than the wavelength, then you are going to see many fringes. But that too, the central fringe will be bigger, something like this. This is what you're going to see. But the moment your B is equal to the wavelength, you are going to see the entire screen filled with it. You are going to see the entire screen filled with it. The light is going to spread everywhere. I'll tell you something which no other teacher would have told you also. What if B is less than lambda? What if B is less than lambda? Now comes the funny part. What if B is less than lambda? Yes, this B is less than lambda. So think what will happen over here. Sine theta, which is n lambda by B, because B is less than lambda, this will be a number more than 1, and n will at least be 1. No, n will at least be 1. No. So what will happen is, because this number will be more than 1, you will see sine theta will be more than 1, meaning the first minima is out of the screen. Is out of the screen. This is crazy. At least here what happened is the minima ended somewhere here at the end of the screen. But here what will happen is that you will see that the minima is out of the screen. That means it will be spread even more, and it will be even more prominent, you can say. It will be even more prominent. Yeah. So that is the idea behind this. So when the when the uh, slit's width is even smaller than the wavelength, it will spread like crazy. It will spread like crazy. Okay. And even the minimas will be out of the screen. So the maxima has spread maximum. Okay. That is the concept behind it. So that's why we say diffraction is prominent when aperture is close enough to the wavelength. When it is close enough to the wavelength. That is the logic behind it. Okay. So now let's talk about polarization. That is the end of the light waves chapter, and let's see it. It's not that difficult. Okay. I just hope I will be able to wake up tomorrow, because I think I'll be taking the class almost till 12 o'clock. I'm not really sure, but I will try to wake up. Okay. In case anything, I will message you in the morning, but 99% I will wake up. Okay. And only if you comment, guys. I mean, if you don't attend the class, then I will feel very bad that after so much of struggle, I'm waking up and taking class for you, and you don't wake up. I will feel very dissatisfied, demotivated, I would say. Yeah, in incoherent, it is just the sum of intensity. Okay. What advice I'll give you last moment, man? My throat is aching now. Hold on. Focus on the class. So much of things I have to explain. Now, what is this polarization and unpolarization? See, transverse waves only will show this property where the, like the electric field, or let's say it's a wave on a string, that particles or that physical quantity will oscillate perpendicular to the direction of the motion, because in transverse waves only the motion of the particles is perpendicular to the wave propagation, and when it oscillates in a peculiar direction, that direction defines that okay, that light is polarized, or that transverse wave is polarized. Sometimes the oscillations are in a one unique direction. Sometimes they oscillate once like this, then they oscillate like this, then they oscillate like this, then like this, then like this. So it is random, because every time the wave might oscillate in different directions. Such a light is then called unpolarized light. The regular light that you see around you is always unpolarized, like the light from the sun, the light from the tube light, the light from the computer screen. They're all unpolarized lights. The direction of the oscillations is not fixed. It is all random. When I say oscillation, whose oscillation? I am talking about the electric field's oscillation. So the light is an electromagnetic wave, So the electric field is oscillating once like this, once like this, once like this. So when it is completely random, it is then said to be unpolarized. The symbol for that is you show some 6 or 8 arrow marks in all directions. It shows that the oscillations is happening in all possible directions. So it is unpolarized. So most of the light from your candle bulb, sun, etc., they are unpolarized in nature. Whereas plane polarized light, in that the electric field or the magnetic field or whatever that quantity which is oscillating in one unique direction and it is not changing. Like take the example of this wave. It's a light wave, it's an electromagnetic wave, electric field is going up and down. The wave is going like this. The wave is going in this direction, but the oscillation is happening here and it is not changing. And it is constantly happening in the yx plane. So xy plane is called as the plane in which the light is being polarized. The plane in which the light is being polarized. X-axis is the direction in which the light is moving. Y-axis is the direction in which the electric field is oscillating. So direction in which it is going, direction in which it is oscillating, if you combine both of them, that plane is called as the plane of polarization. If the light were to go in z direction, then yz plane would have been the plane of polarization. Keep that in mind. The plane containing the electric field and the direction of propagation. So that light can also exist and we can make it using some filters called as polarizers. Sometimes it can be natural also. Now, how do you do it? Here is the logic. So there are some compounds, some organic compounds, sometimes some crystals, some liquids, where when light is passed through it, especially unpolarized light, that crystal, which is also called as a polarizer, has something called as transmission axis. Meaning, all the oscillations which are in that direction, or even if it is at an angle, then there will be some component of it in that direction. Only those components or those oscillations are passed. That's why it is called transmission axis. So the final outcome is that parallel to the transmission axis, you will get a light which is being polarized in the same direction. So unpolarized light becomes polarized when passed through a polarizer. Polarizer has a transmission axis. If you tilt the transmission axis, automatically the plane of polarization will change. Now it so happens that if the original intensity of the light was I naught, the final light which is polarized is I naught divided by 2. I naught divided by 2 in intensity. That's something which is obvious because out of the two planes, only one plane is passing, the other plane is completely cut out. So half of the light is passing through, half of the light is being absorbed by the polarizer. So that is the logic behind I naught by 2. Is this clear? Okay. How come how come it becomes half? Think of it like this. Every oscillation that you take, whether like this or even like this, it will have two components, one in this direction, one in this direction. All these components get cancelled, only these components get added up. So half of the components are cancelled, only half of them is passing for every plane in which the light wave is oscillating. So half is out, half is in. So I naught by 2 is out, I naught by 2 is passing by. Is that now clear? Okay, very good. Joshi, it's from my own question bank and our team's question bank only. Okay. Does the direction of the plane of polarization mean the direction of electric field or the direction of propagation? The direction of plane of polarization never has a direction. It's a plane, remember. The plane will contain two lines. The plane will contain two lines. One, direction in which light is going. Second, direction in which the electric field is oscillating. So those two lines together make a plane. Remember, plane is always made by two lines. So those two lines are speed of light, direction that is, and second, electric field oscillation. Is that now clear? Sir, how only half is there angle involved? See, think of it like this, man. Think of it like this. One is like this oscillating, one is maybe small angle, one is maybe large angle, one is maybe even like this, one is like this, one is even more like this, one is again like this. So for everything, now there is no x component, only y component. Here it has y and some x, little y, more x, only x, here only y, more of x, less of y, somewhat x, somewhat y, complete x, complete y, no x. So do you see over a complete circle, like all the possible directions, all components if you take, more y, lesser y, 0y, less y, more y, 0x, little x, more x, lesser x, no x. So if you see the average, what is happening? If you see the average, what is happening? If you add up all the y's and if you add up all the x components, they will be equal in amount. Is that right? So all the y's and all the x's, they both will be equal in amount. So that is why when they pass through a transmission axis, that will only allow this, that will cancel out this, which is exactly half. Now is it clear? Why it is half and why not 1/4 or anything else for that matter? Because the components will be spread out in all the possible directions. So if there is a y component of large amount, there is a x component of equally large amount. If there is y component of small amount, there is a x component of small amount somewhere else. So equal number of components are there throughout that unpolarized light. Think of it like that. Okay. Sir, unpolarized light is giving polarized light. Okay, fine, sir. But what happens if I put one more polarizer in front of it? So that is Malus law. Now, if the transmission axis is parallel, then all the light will pass through. There is no doubt about it. But somebody does Kida and the transmission axis is perpendicular to this polarized light, then nothing will come out of it. But if it is at an angle, this is what you will see. So unpolarized light became polarized. Let's say 2I0 became I0. Example, it became half. If there is a further Polaroid, which is at an angle, the transmission axis, the final light will only have those electric fields which are in the direction of transmission axis, but the field will be only a component of it. The electric field amplitude will be only a component of it. And remember, intensity is proportional to the square of the amplitude. So that's why the final intensity is original intensity into cos square theta, because intensity is proportional to square of the amplitude. Okay, so that's the crazy part. Intensity becomes cos square times, not cos times, cos square times. Amplitude becomes cos times, intensity is square proportional, so cos square times the older intensity. That's the logic behind it. So Malus law says that if the transmission axis is as it is to the plane polarized light, all the light will pass through. But if you change the Polaroid at 90 degrees, then no light will pass because cos 90 is 0. If it is at an angle, then cos square times theta intensity will pass. That's the logic. We can do some questions and then we'll come to Brewster's law. We can do this. Two Polaroids are oriented with their planes perpendicular to the incident light and transmission axis, making an angle of 30 degrees with respect to each other. What fraction of incident unpolarized light is transmitted? Okay, so what it means is This is one Polaroid. I will turn it. This was the transmission axis. Now you have turned it. Okay. So the first light that you had was unpolarized. This is unpolarized light. The original intensity would be I. When you pass through the first Polaroid, only this transmission axis along the light will pass. So whatever I was there, it will become I by 2. Now you have tilted it by an angle of 30 degrees. So the final light that will come will also be parallel to the transmission axis, the oscillations. So that will be I by 2. Malus law says cos square 30. So cos 30 is root 3 by 2. So root 3 by 2 square. So it will become 3I. 4 into 2 is 8. 3I by 8 is the final intensity. But question is, what fraction is transmitted? So the fraction percentage will be how much ever got transmitted by the initial multiplied by 100. That will be in percentage. How much went on how much was sent into 100. So it will become 3 by 8 multiplied by 100 percentage. Now how much is 3 by 8? 8 by 3. Come on, my dear warriors. How much is it? Answer quickly in the chat box. Yo, 8 threes are 24. So 37 only I think is possible. So yes, 37.5%. Correct. That should be the answer, I believe. Yeah, it is. It is 37.5%. Very good. Very simple it is. Okay. So that's how you use Malus law and that formula. There is one more question coming up on your screen, and here it is. This is a beautiful question which was asked this year, 2025. Two polarizers are placed in such a way that the intensity of the light will be 0. How is that possible, P1 and P2, if they are giving 0 intensity? It just means that both those polarizers are at 90 degrees. So one plane is perpendicular to the other plane. Okay, that's one. P1 is perpendicular to P2. Now a third polarizer is inserted in between P1 and P2 at a particular angle such that the transmitted intensity of the light passing through all the polarizers is maximum. Yo, simple. Okay, so take this and you are rotating it. The angle I do not know how much it is, but if this is theta, then between these two it is 90 minus theta, because both of them are perpendicular. So theta and 90 minus theta. So the angle between P2 and P3, this is P3. So what is the angle between P2 and P3 is the question. So what is happening is, first you are sending in unpolarized light. That first of all becomes polarized. Then it becomes polarized at an angle. And then further it gets polarized over here like this. So this is what is basically happening. So first intensity would be I, or whatever. Then this will be I by 2, of course. Next will be I by 2 cos square theta. I by 2 cos square theta. The final intensity will be I by 2 cos square theta's cos square 90 minus theta, because that is the angle between this light and this light. So cos square 90 minus theta. So this will become I by 2 as it is cos square theta. Cos 90 minus theta is sin theta. So sin square theta. So this will become I by 2 cos theta sin theta, and then you have whole square. Cos theta sin theta, I have an idea. Multiply by 2 and then divide by 2. So So what will happen because of that? 2 square is 4. So I divided by 2 multiplied by 4 multiplied by 2 cos theta sin theta is basically sine 2 theta whole square. So if I want the final intensity to be maximum, I cannot change this. This has to be maximum. That means sine 2 theta's value is maximum when 2 theta is 90 degrees. That means theta is 45 degrees. This is like the range formula, I believe. So angle between this and this is 45. Obviously, between this and this also will be 45 degrees. So 45 degrees is as good as saying pi by 4 radians. So pi by 4 radian is option C. There you go. Pi by 4 is option number C. Simple, easy. What a brilliant question, isn't it? Loved it? Oh, very good. Now let's go to the final part of this, where after Malus law, you see polarization can also occur when you reflect light from a denser medium. Now, when light is falling on a medium, part of it gets transmitted, a part of it gets reflected. Just like sunlight coming and falling on seawater. Some seawater will enter into the ocean, some seawater will reflect back. Natural. Even when light falls on glass, some light will pass through the glass, some light will reflect from the glass. Now, if you choose the angle of incidence in such a way that the reflected light and the refracted light are perpendicular, they found that the reflected light becomes plane polarized. The reflected light becomes plane polarized. That is very, very important. So, yeah, this particular light ray, instead of having oscillations in both the directions, then it becomes plane polarized. So, the reflected light has vibrations which are inside and outside like this, perpendicular to the plane of incidence. The refracted light has more vibrations along that particular plane of incidence. But if you adjust this angle, you can completely get rid of this. So all that will be left is inside and outside oscillations only. So the circle represents oscillations in and out, like cross and dot, and this one is within the plane of the board. So usually the reflected light has more of dots, refracted has more of the planar oscillations, but only when the eye is such that this becomes perpendicular, then you will see that only the dots are there, it becomes plane polarized. So that is basically Brewster's law. When the angle of incidence becomes so that, the reflected and the refracted rays are perpendicular to each other. So this is very important. These two are perpendicular to each other. Then this light becomes completely polarized. So now this becomes polarized light. The reflected light is polarized. This angle at which it happens is such that tan of I is the refractive index, that is also called as Brewster's angle. What is it called? That angle tan of I is mu is called as Brewster's angle. Otherwise, if it is not, then it is not completely polarized. It is partially polarized. That is very important. Okay. All right. All right. Okay. Perfect. So with this, I think we can solve some questions based on this. Yeah. This was a statement-based question. If Brewster's angle for light from air to glass is theta b, then the Brewster's angle for light propagating from glass to air is theta by 2 minus b. Brewster's angle for light propagating from glass to air is tan inverse of mu g, where mu g is the refractive index of glass. What do you think is correct? Come on, think, guys. This is not that difficult. I just told you light should be falling on a denser medium. So whatever gets reflected gets polarized. it should be falling on a denser medium. But when it goes from glass to air, it is dense to rare. That can't happen. So actually saying Brewster's angle for glass to air, wrong. It can't happen. Both the statements should be wrong, I believe. Oh, wait. Then the Brewster's angle for light propagating from glass to air is theta 2 minus b. Both statements should be false, guys. I think they have made a mistake over here. Yeah, but you know, if you are going from air to glass, Brewster's angle is theta b. If you are going from glass to air, it will not happen only. Yeah, both statements should be basically false. Both statements should be false. Moving ahead to the next question. This one, let's see if we can solve this. If polarizing angle of a medium is theta, speed of light is v, angle between theta and v is how much? Polarizing angles means Brewster's angle, guys. They're just telling Brewster's angle. Come on, think about it. Think about it. What will be the correct answer? Hmm. Polarizing angle means Brewster's angle. Brewster's angle. So we all know tan of Brewster angle will be refractive index, and refractive index is speed of light in vacuum upon speed of light in that medium. So if that is the case, theta will be simply tan inverse of C divided by V. Tan inverse of C divided by V, which is the same as cot inverse of V by C. Cot inverse of V by C, which is C option. So I think C option should be correct. So just played around with mathematics a little bit here and there. Yeah. No, it is not hard. It is actually very simple. This was just refractive index definition. No? We all know speed of light is speed of light in vacuum divided by refractive index. So from this we get this. Okay. So that was that particular question, and we are done for the day with almost close to 5.5, 6 hours marathon. Okay. I hope you enjoyed the class. You learned a lot from the basics, every single thing. We did problems also for every single concept. So I think this is one of the best classes for view optics. Forget in English, even in general. Okay. So spread the message, comment below how much you loved the class. Also, I would love to see some nice things from you. What are you doing and any doubts also. And also I've given a homework question, solve that. Okay. Thank you so much. Have a great time. Take care. This was Captain Shreyas signing off. Hasta luego.